Hello there and welcome to Physics with William, where curiosity gets cozy and science takes the scenic route to slumber. Tonight we're drifting toward one of the strangest ideas in all of modern physics, a thing that sounds as though it belongs in science fiction, in a starship engine room or perhaps locked away in a glowing glass chamber somewhere beneath a mountain. And yet it is real. It is measured, created, studied, trapped, lost, feared, and used. Tonight our gentle journey is all about antimatter. Antimatter is one of those words that feels heavy before we even understand it. It has a quiet drama to it. Antimatter. Matter, but not quite matter. The opposite of the stuff that makes the chair beneath you, the air around you, the tea cooling beside you, the blanket pulled around your shoulders, and the sleepy little planet turning beneath all of us. It sounds like a cosmic shadow, a mirror version of reality, the universe looking at itself and finding another face staring back. And in a way, that is not a bad place to begin. Because antimatter is not just nothing. It is not empty space. It is not darkness. It is not some magical substance that cancels reality because it has a bad attitude. Antimatter is real matter of a different kind. It has mass. It can move. It can be shaped into particles. It can even form atoms, at least for brief and carefully controlled moments. If you could hold it safely, which you absolutely cannot, it would not look like a ghost or a cloud of purple lightning. It would be built from particles, just as ordinary matter is built from particles. The difference is that those particles carry certain properties flipped the other way around, like a glove turned inside out, or a photograph printed as a negative. Before we wander into the deeper mystery, I would love to know where in the world you are listening from tonight. Are you tucked away in a quiet room, with the lights low and the day finally slowing down? Are you somewhere early in the morning, letting science keep you company before the world gets loud again? Or are you listening from some small pocket of midnight, where the house is still, the clock is patient, and even the universe seems to speak more softly? Tell me, if you like, where are you listening from, and what does the sky look like outside your window right now? It feels fitting, does it not? A video about antimatter, this strange hidden twin of ordinary matter, reaching listeners made entirely of matter, scattered across a planet that somehow survived a cosmic beginning where matter and antimatter should have met like perfect rivals. And if you find this quiet voyage soothing, intriguing, or just a pleasant place to rest your thoughts for a while, I would be ever so grateful if you gave the video a like and maybe subscribed. It helps this calm little corner of physics drift a little farther, reaching others who might enjoy a slower kind of science, the kind that does not shout for attention, but sits beside you with a warm drink and says, "Let us think about the universe for a bit." I do hope tonight's topic is not so interesting that it keeps you awake, but if it does, well, at least you will be awake with one of the most elegant mysteries physics has ever found, and that is not the worst company to have. So settle in, let your shoulders soften, let the day loosen its grip, and let us begin with a simple thought. Everything around you is made of matter. That seems obvious enough. Your hands, your hair, your bones, the floorboards, the moon, the stars, the little dust particles floating in a beam of afternoon light, all of it is matter. Matter is the familiar substance of existence, the cosmic furniture, the stuff that gives the universe its touchable shape. But physics, being physics, is rarely content to leave familiar things alone. When scientists began looking more closely at the tiny ingredients inside matter, they found not only particles, but a strange kind of symmetry. For many of those particles, there seemed to be another possible particle, a partner, almost identical in mass, but opposite in electric charge and some other hidden qualities. The electron, for example, has a partner called the positron. The electron is one of the most common particles in your body. It hums through atoms, helps build chemistry, carries electricity, and generally does a great deal of quiet work while receiving very little applause. The positron is almost the same as the electron in mass, but it carries the opposite electric charge. It is not an electron wearing a tiny villain cape, though the image is admittedly charming. It is the electron's antimatter counterpart, a mirror particle. A proton has an antimatter counterpart too, called the antiproton. A neutron has the antineutron. And if you build these antiparticles together carefully enough, you can make antiatoms. Antihydrogen, for instance, is the antimatter version of hydrogen. Ordinary hydrogen is made from a proton and an electron. Antihydrogen is made from an antiproton and a positron. It sounds simple, almost tidy, like swapping the labels on a pair of drawers. But the moment matter and antimatter meet, the universe does something dramatic. They annihilate. Now, that word is a little fierce for a sleep science video, I know. Annihilation sounds like something that should be accompanied by alarms, flashing red lights, and perhaps a nervous engineer shouting into a radio. But at the particle level, annihilation means that when a particle meets its antiparticle, the pair can transform into energy, usually in the form of light or other particles. The matter does not simply vanish into a magician's sleeve. It changes form. It becomes something else. The mass and energy are balanced. The cosmic bookkeeping is kept. And the universe, as usual, refuses to let anything simply disappear without filling out the proper paperwork. Still, there is a quiet violence to it. Matter and antimatter cannot comfortably share the same room, at least not for long. Put an electron and a positron together, and they do not settle down, discuss their differences, and start a tiny household. They destroy each other and release energy. This is why antimatter has such a powerful reputation. It is not because antimatter is evil. It is because ordinary matter and antimatter are not stable neighbours. They are opposites in a way that becomes explosive when they touch. And that raises a very natural question. If antimatter is real, where is it? Why do we not see anti-rocks, anti-trees, anti-teacups, or anti-pigeons with suspiciously reversed personalities? Why is the universe around us made almost entirely of matter, instead of being half matter and half antimatter? And why, if the early universe should have made both in nearly equal amounts, is there anything left at all? This is where antimatter changes from a strange particle idea into one of the deepest mysteries in cosmology. In the earliest moments after the beginning of the universe, conditions were unimaginably hot and dense. Particles and antiparticles were being created and destroyed in a furious storm of energy. According to our best understanding, matter and antimatter should have appeared in almost equal amounts. If everything had been perfectly balanced, matter and antimatter would have wiped each other out, leaving behind a universe filled mostly with radiation, a vast glowing emptiness with no galaxies, no planets, no chemistry, no oceans, no late-night snacks, and certainly no one lying in bed wondering what antimatter really is. But that is not what happened. Something tipped the balance. For every great crowd of matter and antimatter particles that destroyed each other, a tiny surplus of matter survived. A very tiny surplus. But in a universe as large as ours, tiny is more than enough. That little leftover became everything. It became stars, planets, nebulae, comets, oceans, skin, stone, books, bread, and the sleepy listener hearing these words right now. You are made of the leftovers of an ancient imbalance. You are matter that somehow won a cosmic coin toss, though perhaps one is too simple a word. The truth is, physics still does not fully know why matter survived. This is one reason antimatter feels so haunting. It is not just a curiosity, it is a clue. It points back to the beginning and asks why the universe chose this shape rather than another. Why is there something instead of almost nothing? Why does ordinary matter dominate? Why did the great mirror not cancel itself out completely? Antimatter is not only the opposite of matter, it is a question built into the foundations of existence. The story of antimatter did not begin with someone finding an anti-pebble lying around in a laboratory drawer. It began in the strange marriage between quantum physics and relativity, when scientists were trying to understand how tiny particles behave when they move very fast. In the early 20th century, physics was already having a rather dramatic identity crisis. Newton's steady mechanical universe had been shaken by Einstein. Quantum mechanics was making particles behave like waves, probabilities, and tiny indecisive whispers. And into this already unsettled room came an equation that suggested the electron had a hidden twin. The British physicist Paul Dirac was trying to describe the electron in a way that respected both quantum theory and Einstein's special relativity. What emerged from his work was not just a better description of the electron, but the prediction of something unexpected. The mathematics allowed for a particle like the electron, but with positive charge. At first, this was deeply strange. It was as though the equations had opened a cupboard and found an extra cup nobody remembered buying. But in physics, when the mathematics points towards something new, the universe sometimes has the unnerving habit of already having placed it there. A few years later, the positron was observed in cosmic rays. High-energy particles from space were striking Earth's atmosphere, producing showers of other particles, and among them was this positively charged counterpart of the electron. The antimatter twin was not merely an artifact of calculation, it was real. The mirror had answered. There is something lovely about that in a very physics sort of way. A human being follows a chain of thought, writes down a mathematical description, notices that it implies something odd, and then nature quietly says, yes, that is here too. It is almost as if the universe keeps a set of hidden doors, and mathematics is one of the keys we have learned to use. Not always perfectly. Sometimes we jiggle the lock for decades. Sometimes we open a broom closet and call it a breakthrough before realizing our mistake. But sometimes, as with antimatter, the door opens onto something real and astonishing. Since then, antimatter has moved from prediction to experiment to technology. We create tiny amounts of antimatter in particle accelerators. We detect it in cosmic rays. We use positrons in medical imaging, where they help doctors look inside the body. This is one of those facts that sounds almost too strange to be true. The same kind of particle that helps us ask why the universe exists is also used in hospitals to find illness. Antimatter, the dramatic mirror substance of physics, has a day job in medicine. It is rather humbling, really. The universe's deepest mysteries sometimes end up helping with very practical things, like scanning tissues and guiding treatment. There is antimatter in space too. Not great anti-galaxies that we have confirmed, not vast kingdoms of anti-stars shining in reverse, but individual antiparticles created by energetic events. Cosmic rays can produce antimatter. Certain radioactive decays can produce positrons. Even thunderstorms have been connected to bursts of antimatter-related particles. The world above us, with its clouds and lightning and rumbling weather, is stranger than it looks. Somewhere in the violence of a storm, nature can briefly make particles that sound as though they belong on the far side of reality. But antimatter is hard to keep. Very hard. Since our world is made of matter, antimatter cannot simply be placed in a bottle. The bottle is made of matter, and antimatter is not famous for its ability to politely avoid the walls. Charged antimatter particles have to be held in electromagnetic traps, suspended so they do not touch ordinary material. Neutral antimatter atoms, like antihydrogen, are even trickier, because they do not respond as easily to electric fields. Scientists use extremely careful magnetic arrangements to hold them for study. It is a bit like trying to store a snowflake made of lightning inside a cage made of invisible hands, and the amounts are tiny. Very tiny. When people imagine antimatter, they often think of enormous engines, world-ending bombs, or sleek starships crossing the galaxy on beams of pure energy. The reality is far more delicate. Laboratories produce antimatter in minuscule quantities, and it takes enormous effort and energy to do so. The antimatter we can create is not sitting around in large glowing tanks, waiting for someone with a dramatic haircut to steal it. It appears in tiny traces, carefully counted, carefully trapped, and often gone almost as soon as it arrives. That does not make it less important. In fact, the difficulty is part of the wonder. We're made of matter, living on a matter planet, using matter tools, trying to understand the mirror version of matter without letting it touch anything. That is a wonderfully human problem. It is also the sort of problem physics seems to enjoy handing us. Here is a substance that could help explain why anything exists, but it destroys itself when it meets your equipment. Good luck. And yet, we keep studying it. Scientists compare hydrogen and antihydrogen to see whether they behave exactly the same except for their reversed properties. They ask whether antimatter falls under gravity in the same way ordinary matter does. Recent experiments strongly suggest that antimatter does fall downward, as expected, but the precision continues to improve. It may seem obvious that antimatter should fall like matter, but in physics, obvious is not the same as tested. The universe has surprised us before, so we check, we measure, we build careful machines and ask gentle, exacting questions. Does the mirror obey the same rules? Does it respond to gravity the same way? Does it carry some tiny hidden difference that might explain the cosmic imbalance? That last possibility is especially important. Matter and antimatter appear almost perfectly symmetrical, but almost is a dangerous word in physics. A tiny difference, almost too small to notice, may have shaped the entire universe. If matter and antimatter behaved with perfect symmetry in every respect, then the early universe's imbalance would be very hard to explain. But if there were slight differences in how particles and antiparticles changed, decayed, or interacted, those differences might have given matter its narrow advantage. Physics has found some examples of these symmetry differences, but not enough to fully explain the matter-rich universe we see. The mystery remains open, quietly waiting. So when we ask what antimatter really is, we're not only asking for a definition, we're asking why reality has a mirror, why the mirror is mostly missing, and why the side we live on survived. We're asking why the universe did not erase itself in its first hot breath. We are asking what laws govern the tiny opposites hiding behind familiar matter. Antimatter is not just a substance, it is a reminder that the ordinary world is less ordinary than it seems. Look around you for a moment, even if your eyes are closed and you're only imagining the room. The bed, the lamp, the phone, the walls, the floor, the small collection of things that make up your evening. All of it is matter, calm, stable, everyday matter. It does not glow with cosmic importance. It does not announce that it survived a primordial struggle. It simply sits there, being a mug, a pillow, a curtain, a hand resting on a blanket. But inside that ordinary stillness is a deep historical fact. This matter exists because somewhere at the beginning, the balance was not exact. That is the strange comfort of antimatter. It makes the universe feel delicate, but also generous. Had the early balance been perfect, there would be no stars to warm planets, no carbon chemistry, no quiet evenings, no voices telling stories about physics. A tiny imperfection became the possibility of everything we know. The universe, in its first moments, was not perfectly symmetrical. And because it was not perfect, we are here. Perhaps that is why antimatter has such a hold on the imagination. It sits at the edge between destruction and creation. When it meets matter, it releases energy. When it appears in theory, it reveals symmetry. When it appears in experiments, it tests the deepest laws we know. When it appears in cosmology, it asks why the universe exists in this lopsided, matter-filled way. It is both a mirror and a missing piece, both a practical tool and a cosmic riddle. And as we move more deeply into the story, we will see that antimatter did not arrive as a wild guess or a fantasy. It came from physics itself, from the attempt to understand the electron, from equations that seemed to whisper of an opposite particle before anyone had seen one. That may be the most remarkable part of all. Long before antimatter was trapped in laboratories or used in medical scans, it appeared as an idea forced into view by the structure of the theory. The universe had placed a shadow inside the mathematics, and patient minds began to follow it. At first, antimatter sounds like it should be the opposite of existence itself, as though ordinary matter is the thing that says yes, and antimatter is the thing that says no. The name does have a wonderfully dramatic flavour. It feels like something a villain might keep in a silver container, or something a starship engineer might mention just before everyone looks worried. But the real story is gentler, stranger, and in many ways more beautiful than that. Antimatter is not the opposite of existence. It is not an absence. It is not a hole in reality. It is matter with certain properties reversed, a kind of cosmic reflection, almost the same shape as the familiar world, but with its signs turned around in ways the universe takes very seriously. To understand why this is so odd, it helps to begin with the ordinary stuff. Matter is everything you can touch, breathe, eat, accidentally drop, or step on in the dark. It is the wooden table, the glass of water, the soft pillow, the bones in your hand, the quiet dust on a shelf that somehow returns 2 days after you clean it. Matter is built from atoms, and atoms are built from smaller particles. In the centre of most atoms are protons and neutrons. Around them are electrons, moving not like tiny planets in neat little circles, but more like soft clouds of possibility, which is the sort of phrase that makes quantum physics sound like it has been awake too late. Now imagine that for each of these familiar particles, nature allows a partner particle. Not a copy exactly, and not an enemy exactly, but a mirror version. The electron has the positron, the proton has the antiproton, the neutron has the antineutron. These antiparticles are not imaginary. They are not bookkeeping tricks. They are as real as the particles they mirror. A positron has the same mass as an electron. It can move through space. It can be detected. It can leave tracks in instruments. But where the electron carries negative electric charge, the positron carries positive electric charge. It is like meeting someone who looks almost exactly like your friend, has the same voice, the same walk, the same fondness for biscuits, but insists on standing on the opposite side of every doorway. The important thing is that antimatter is not made of some different kind of substance in the everyday sense. A positron is not a weird liquid version of an electron. An antiproton is not a proton dipped in cosmic ink. These are particles with the same mass as their ordinary partners, but reversed in charge and in some other deeper quantum properties. If ordinary matter is a sentence written in one direction, antimatter is not silence. It is the same sentence reflected in a mirror, still meaningful, still structured, but turned around in a way that changes what happens when the two meet. And when they meet, things do not remain calm for long. Matter and antimatter are famous because when a particle meets its antiparticle, they can annihilate. That sounds rather alarming, so let us soften the word a little. Annihilation does not mean the universe simply forgets they were there. Physics is not quite that careless. It means the particle and antiparticle transform into other forms of energy, often light, and sometimes other particles, depending on what met and how. The mass they carried becomes energy. The identities they had are gone, but the cosmic accounting remains tidy. Nothing cheats, nothing slips out the back door. The universe, despite all its mystery, is oddly strict about keeping receipts. Still, from our point of view, the result can be spectacular. Matter and antimatter cannot sit comfortably together like two polite guests at a dinner table. If an electron meets a positron, they do not discuss their opposite charges over soup. They transform into energy. If a proton meets an antiproton, the result is more complicated, but the principle remains the same. The meeting of opposites releases what had been locked inside them. This is why antimatter has such a powerful reputation. It is not because antimatter is angry or unstable by itself. In isolation, antimatter can behave perfectly normally. The problem is that our universe is filled almost entirely with ordinary matter. Antimatter is the rare visitor at a party where every wall, chair and teacup is made of the thing it must not touch. This is one reason antimatter feels so difficult to imagine. We live in a matter world. Our hands are matter, our tools are matter, our containers are matter. If you made a tiny piece of antimatter and dropped it into an ordinary box, the box would not hold it. The antimatter would touch the matter of the box, and that would be the end of the arrangement. So scientists cannot store antimatter the way you might store sugar in a jar or buttons in a tin. They must use fields, careful, invisible arrangements of electricity and magnetism, to hold charged antimatter away from the walls. It is a little like keeping a soap bubble from touching anything, except the soap bubble is made of a particle mirror of reality, and the room itself would destroy it on contact. Quite a fussy house guest, really. But if antimatter is so reactive with matter, why do we think of it as ordinary in its own way? The answer is that antimatter follows rules. It is not chaos. A positron responds to electric and magnetic fields in predictable ways. Antiprotons can be slowed, trapped, and studied. Antihydrogen can be formed from antiprotons and positrons, creating the antimatter version of the simplest atom. For tiny moments in carefully designed experiments, scientists can make a little antiatom and ask it how it behaves. Not in words, of course. Antihydrogen is not known for giving interviews, but by measuring its light, its motion, and its response to gravity, researchers can test whether it truly mirrors ordinary hydrogen. This leads to one of the most important ideas in antimatter physics. If matter and antimatter are perfect opposites in the right way, then an anti-atom should behave like an ordinary atom under the same physical laws, except with charges reversed. Antihydrogen should have the same structure as hydrogen. It should produce the same patterns of light. It should fall downward under gravity, just as ordinary matter does. These things sound obvious, but science has learned not to trust obvious too much. Obvious once told us that Earth was still and the sky moved around it. Obvious once told us that time passed the same for everyone. Obvious is a useful neighbour, but not always a reliable witness, so scientists test antimatter with great care. They compare it to matter. They look for tiny differences. They search for some hidden imbalance, some slight crack in the mirror. Because if antimatter behaved exactly like matter in every way, except for the flipped properties we already know, then one of the greatest mysteries in physics becomes even harder to explain. That mystery is the survival of matter itself. The early universe should have made matter and antimatter together. Energy in those first hot moments could become particles and antiparticles, appearing in matched pairs, and whenever those pairs met, they could annihilate back into energy. If the universe had been perfectly balanced, matter and antimatter would have destroyed each other almost completely. There would be no stars, no galaxies, no planets, no chemistry, no warm kitchens, no sleepy science channels, no one wondering whether they should listen for 5 more minutes before finally going to sleep. The universe would have been a very different place, mostly radiation, with almost none of the matter needed to build anything solid. But here we are. The universe clearly did not cancel itself perfectly. Matter survived. Antimatter, at least on large scales, mostly did not. Somewhere in the earliest moments there was a tiny imbalance. For every vast number of matter and antimatter particles that annihilated, a small excess of matter remained. That excess became everything we see. Every star is made from that leftover matter. Every planet, every mountain, every cloud, every person. It is a strange thought that all the familiar substance of your life may be the result of a tiny ancient asymmetry, a small cosmic unfairness that made existence possible. This makes antimatter more than a particle curiosity. It makes it a question about why the universe is not empty. When scientists study antimatter, they are not only asking what happens when opposites meet, they are asking whether antimatter holds a clue to the imbalance that gave matter its victory. Perhaps there are small differences between the way matter and antimatter behave. Perhaps some particles decay in a slightly biased way. Perhaps the laws of physics treat the mirror image almost the same, but not completely. That almost is where whole universes can hide. In ordinary life, mirrors are simple. You stand in front of one, raise your right hand, and your reflection raises what looks like its left. The reflection is faithful but reversed. But imagine if, once in a while, the mirror made a tiny mistake. Maybe it blinked a fraction later than you did. Maybe it smiled when you did not. Maybe the reflection was mostly perfect, but not entirely. That would be unsettling in a bathroom mirror. In physics, it could explain why anything exists at all. Antimatter is often described as mirror matter, and that is helpful as long as we do not take the image too literally. There are no anti-chairs floating somewhere behind a glass surface, waiting for their chance to emerge. There may or may not be large regions of antimatter far away in the cosmos, but if there were, they would be hard to hide at the boundaries. Where matter and antimatter met, we would expect intense signals from annihilation. So far, the observable universe appears overwhelmingly made of matter. The mirror is real, but the reflected world is mostly missing. That absence is itself a clue. If the universe can create antimatter, and if antimatter is as real as matter, why did it not remain in equal amounts? Why are galaxies not half made of anti-stars? Why do we not see anti-comets, anti-planets, or anti-dust clouds drifting through space? The answer is not simply that antimatter is impossible. It is possible. We make it. We detect it. Nature makes it too. The answer must lie in the history of the universe, in the earliest reactions and the deepest symmetries of physics. There is another way antimatter surprises people. Because of its reputation, we tend to imagine it as rare in every sense, as though it belongs only in enormous machines or distant cosmic events. But tiny traces of antimatter appear naturally. Certain radioactive processes produce positrons. High-energy collisions in the atmosphere can produce antiparticles. Cosmic rays arriving from space can carry or create antimatter. Even within medicine, positrons are used in imaging, where their annihilation helps create pictures from inside the body. This is one of the more charming contradictions of modern science. Antimatter sounds like a threat to reality, and yet it can help doctors locate disease. The universe is full of things that seem dramatic in name and practical in use, like lasers, radiation, and people who own 3 different kinds of kitchen thermometer. A positron emission scan, for example, relies on the behavior of positrons. A substance is introduced into the body, and as positrons are emitted, they soon meet electrons. Their annihilation produces light in a form that detectors can catch. From those signals, a computer builds an image. The antimatter does not roam freely like a tiny cosmic monster. It appears, interacts, and is gone almost immediately, leaving information behind. In this way, antimatter becomes not just the opposite of matter, but a messenger. It briefly arrives from the mirror side and helps reveal what ordinary matter is doing. That should tell us something important. Antimatter is strange, but it belongs to the same universe. It is woven into the same laws. It is not supernatural. It is not a loophole outside physics. It is physics showing us that reality has more symmetry than everyday experience suggests. We do not encounter antimatter at breakfast because our world is not built from it. But at the particle level, nature keeps the option open. The universe knows how to make both versions. Imagine an ordinary hydrogen atom, the simplest atom of all. It has 1 proton and 1 electron. It is light, common, and enormously important, helping build stars and water and much of the visible universe. Now imagine antihydrogen. 1 antiproton, 1 positron. Same simple structure, but with the charges reversed. If you could place antihydrogen in an antimatter universe, surrounded by antimatter stars and antimatter planets, it might seem completely ordinary. Anti-chemists, if such beings could exist in such a universe, would not call it anti-anything. They would simply call it hydrogen. We call it antimatter because we are the matter side of the story. Our language is biased by where we happen to stand. That is a useful reminder. The word anti can make antimatter sound secondary, like a strange copy of the real thing. But from a deeper perspective, matter and antimatter are partners in the theory. We call ours matter because we are made of it. If the universe had tilted the other way and antimatter had survived instead, then beings made of what we call antimatter might call their stuff matter and ours antimatter. They would be just as correct from their point of view. The labels are local, the symmetry is deeper. There is something almost humbling about that. We think of ourselves as living in the normal universe, and in a practical sense we do. But physics quietly says normal may just mean common where you are. Matter is normal because it won the numbers game. Antimatter is strange because it is rare around us. The underlying laws do not seem to treat antimatter as fantasy. They allow it. They predict it. They invite us to understand why it is missing. The more carefully we look, the more antimatter becomes a kind of cosmic mirror held up to matter. It asks what makes a particle itself. Is it mass? Is it charge? Is it the way it interacts? Is it the direction of its hidden quantum properties? If two particles have the same mass but opposite charge, are they opposites, twins, partners, or reflections? Physics answers not with one simple word, but with experiments. It says, watch how they move, see what happens when they meet, compare the light they produce, build the anti-atom, measure the fall, search for difference, listen to the mirror very closely. And yet, even with all this, antimatter keeps part of its mystery. We understand a great deal about individual antiparticles. We know how to produce them in tiny amounts. We know how to detect them. We know what happens when they meet matter. But the largest question remains open. Why did the early universe leave matter behind? The answer may involve processes we have not fully discovered, particles we have not yet seen, or symmetries that break in ways too subtle for our current instruments. Antimatter is not only a thing we study, it is a pointer toward missing physics. So, what is antimatter really? It is matter's strange opposite, but not in the sense of evil, absence, or nothingness. It is a real form of matter with reversed properties. It is the mirror partner of the particles that build our world. It is a substance that can briefly exist but cannot touch ordinary matter without transforming. It is a tool in medicine, a signal in cosmic rays, a challenge in laboratories, and a clue to the first moments of the universe. It is both familiar and alien, both mathematically expected and emotionally astonishing. Perhaps the gentlest way to think about antimatter is this. The universe has a habit of balancing possibilities. For a particle, there may be an antiparticle. For charge, an opposite charge. For matter, a mirror. But the universe we inhabit is not perfectly balanced in what remains. Something leaned. Something favoured one side by a whisper. And from that whisper came stars, planets, and us. This is why antimatter is not just a dramatic word from science fiction. It is a reminder that reality is built from pairs, symmetries, and broken symmetries. It shows us that the world we call ordinary is only half of a deeper pattern, and the missing half still leaves fingerprints everywhere. The particles in your body have mirror partners that mostly vanished from the cosmic stage, but the story of those partners is written into the reason your body exists at all. The ordinary matter of your hand is not ordinary because it lacks mystery. It is ordinary because the mystery settled into it long ago, quietly, patiently, waiting for us to notice. And once we have noticed that the universe has this mirror side, the next question comes naturally. How did anyone discover such a thing? How did physics move from familiar particles to the idea that every electron might have a reverse companion? The answer did not begin with a glowing sample or a captured anti-atom. It began with thought, mathematics, and young physicists trying to make the electron fit into a universe where quantum rules and relativity both had to be true at the same time. The strange mirror of antimatter did not first appear as a glowing spark in a laboratory, or as a strange mark left inside a detector, or as a tiny flash from the deep sky. It first appeared in thought. More precisely, it appeared in the mathematics of a physicist who was trying to make two great ideas fit together without breaking either one. That is often how physics moves forward, not always with a telescope turned toward the heavens or a machine shaking beneath the floor, but with a quiet mind asking why two truths, both successful in their own worlds, refuse to sit neatly at the same table. By the early 20th century, physics had become a rather lively household. Classical physics was still there, respectable and useful, wearing a waistcoat and trying to keep order. Einstein had changed the meaning of space and time, showing that they were not fixed furniture but part of a flexible fabric. Quantum mechanics had arrived with all the calm of a cat knocking a vase off a shelf, telling everyone that particles could behave like waves, that certainty had limits, and that the smallest parts of nature did not follow the tidy rules that everyday objects seem to follow. It was an exciting period, though perhaps not a restful one if you happened to be a physicist trying to sleep. The electron was already known. It was small, negatively charged, and essential to the structure of atoms. It played a quiet role in electricity, chemistry, light, and nearly every ordinary process around us. But describing it properly was not simple. Quantum mechanics could explain many things about atomic behavior, but there was a problem. The electron was not just a small particle moving gently inside an atom. It could also move very fast, and when things move very fast, Einstein's special relativity has to be respected. Nature does not allow us to use one set of rules when it is convenient, and another set when we are feeling tired. If a theory is going to describe the electron deeply, it must speak both quantum and relativistic at once. That was the challenge facing Paul Dirac, one of the most unusual and brilliant physicists of the 20th century. Dirac was not famous for being talkative. He was famously quiet, precise, almost severe in his use of words. Some people tell stories of him giving answers so short they seemed less like conversation and more like carefully rationed supplies, and yet his mind moved with extraordinary elegance. He had a gift for seeing beauty in mathematics, not beauty as decoration, but beauty as a sign that the theory might be touching something true. To Dirac, a good equation should not only work, it should have a kind of deep inner grace, like a key cut so cleanly that it turns in a lock no one else had noticed. Dirac wanted to describe the electron in a way that combined quantum mechanics with special relativity. Earlier attempts had run into difficulties. The mathematics could produce strange answers, including impossible-looking negative energies, which sounded at first like a very bad sign. In ordinary life, if your bank account has negative money, that is already inconvenient enough. A particle with negative energy seemed far worse. It suggested that the theory might be unstable, that electrons could fall endlessly into lower and lower energy states, like a person discovering a staircase that never reaches the basement and deciding unwisely to keep going. But Dirac did not simply throw the problem away. He followed the mathematics carefully. He looked for a way to make the theory consistent, and in doing so, he found something remarkable. His work implied that the electron had a counterpart, a particle with the same mass but the opposite electric charge. This was not something anyone had ordered from the menu. It simply appeared. The mathematics seemed to insist on it. It was as though Dirac had tried to draw a complete map of the electron and found that the paper continued beyond the edge, showing a country no one expected to be there. At first, the idea was difficult to interpret. Physics is full of mathematical possibilities, and not all of them correspond to things nature actually contains. Sometimes mathematics offers a path that leads to reality. Sometimes it offers a path that leads to nonsense wearing a convincing hat. The challenge is knowing which is which. Dirac initially thought about the strange positive counterpart in a way that connected it to protons, because protons were already known and carried positive charge. But the proton was much heavier than the electron, and that did not fit the prediction. The new particle, if it existed, should be just like the electron in mass, but with the charge reversed. Something entirely new was needed. Imagine how strange that must have felt. The electron was already odd enough. It was not a little ball in any simple everyday sense. It behaved according to quantum rules, surrounded by probabilities, wave behavior, and the strange discipline of atomic structure. And now the mathematics suggested that nature might contain an anti-electron, a positively charged twin, not a proton, not a familiar atomic ingredient, a new particle that no one had yet seen. It is the sort of idea that might make a cautious scientist clear their throat and say, perhaps we should check this very carefully before becoming too excited. The universe, however, was already preparing its reply. The evidence came from cosmic rays, high-energy particles arriving from space and striking Earth's atmosphere. Cosmic rays are like tiny messengers from violent places. They come from the sun, from distant stars, from supernova remnants, and from energetic regions of the universe where particles are accelerated to extraordinary speeds. When these cosmic particles hit the atmosphere, they create showers of secondary particles. To study them, scientists used instruments that could reveal the paths of charged particles, often through trails left in vapor or other sensitive materials. These tracks were delicate signatures, little curves and lines showing how particles move through magnetic fields. In the early 1930s, Carl Anderson was studying cosmic rays using a cloud chamber. A cloud chamber is one of those scientific devices that feels almost magical, even though it is entirely physical. Inside it, charged particles passing through supersaturated vapor leave thin trails, like the wake of an invisible boat moving through mist. Place the chamber in a magnetic field, and the paths of charged particles bend. The direction and curvature of the bend reveal the particles' charge and momentum. It is a little like watching footprints in snow, and learning not only that someone passed by, but how heavy they were, how fast they walked, and whether they preferred turning left at the biscuit cupboard. Anderson found a track that looked like it had been made by a particle with the mass of an electron, but the opposite charge. This was the positron, the anti-electron. Dirac's strange mathematical prediction had stepped into the world of observation. The mirror particle was real. There is a deep pleasure in that moment, not loud pleasure, not fireworks, though the discovery certainly deserved some, more like the quiet click of a lock opening. An idea born from the need to make a theory whole had found its counterpart in nature. Dirac's mathematics had not been merely clever, it had been pointing towards something that existed. And this is one of the remarkable things about physics. Sometimes, when the theory is built with enough care, enough respect for what is already known, and enough openness to what seems strange, it can predict pieces of reality before our instruments have met them. The positron's discovery changed the meaning of Dirac's work. It showed that antimatter was not just an abstract possibility. It was part of the particle world. The electron had a partner. The mirror was not imaginary. And once the positron was found, physicists began to understand that antimatter might be a much broader principle. If the electron had an antiparticle, perhaps other particles did too. Over time, this proved to be true. The antiproton was discovered later. The antineutron followed. Eventually, scientists could create and study more complex forms of antimatter, including antihydrogen. But the first great door opened with the positron, that small positive shadow of the electron. It is worth slowing down here, because the story is easy to rush. The prediction did not come from someone saying, "What if there were opposite particles, because that would sound interesting?" It came from trying to obey the rules physics already knew. Quantum mechanics had to be respected. Relativity had to be respected. The electron had to be described properly. And when Dirac found a way to do this, the structure of the solution included an unexpected partner. In that sense, antimatter did not enter physics as a decoration. It was demanded by consistency. The theory made room for it because the theory could not be complete without it. That is why scientists often speak of mathematical beauty with a seriousness that may sound odd from the outside. Beauty in physics is not about prettiness or personal taste, at least not only that. It often means simplicity joined with power. It means a theory explains many things without being patched together like an old coat. It means the pieces fit in a way that feels inevitable once seen. Dirac's work had that quality. It united ideas that had seemed difficult to combine, and in doing so, it revealed something hidden. The positron was not added afterward. It was already there in the logic of the theory, waiting for experiment to catch up. Still, one should be careful. Physics is not magic, and equations are not crystal balls. Not every mathematical result predicts a real object. The universe is not obligated to act out every interesting line written on a chalkboard. That is why experiment matters so deeply. Dirac's prediction became science in the stronger sense because it could be tested, and then it was. The positron track in a detector was not a philosophical mood. It was evidence, a curve in a chamber, a signal left by a real particle moving through real space. The discovery also changed the emotional texture of physics. Before antimatter, one might have imagined particles as individual ingredients, each discovered one by one, like minerals in a cabinet. After antimatter, particles began to look more like members of a deeper pattern. For every kind of particle, there might be a partner written into the underlying rules. Matter was no longer simply a collection of tiny things. It was part of a balanced structure, a structure with reflections, reversals, and symmetries. The world had become more orderly and stranger at the same time, which is a very physics thing to do. The positron itself soon found practical importance. In certain radioactive processes, positrons are produced naturally. When a positron meets an electron, the two annihilate and produce light in a very specific way. This behaviour later became the basis for medical imaging techniques that can help doctors see inside the body. So a particle predicted from deep theory, first observed in cosmic rays, eventually became part of a tool used in hospitals. There is something wonderfully winding about that path. A quiet physicist studies the electron. An equation suggests a mirror particle. A cosmic ray leaves a track in a chamber. Decades later, the same kind of particle helps reveal what is happening inside living tissue. The universe often refuses to keep pure wonder and practical usefulness in separate drawers. But the positron was only the beginning. If there were anti-electrons, what about antiprotons? A proton is much heavier than an electron and carries positive charge. Its antiparticle, the antiproton, would have the same mass but negative charge. Finding it was far more difficult. It required more powerful machines because creating heavier antiparticles takes more energy. In the mid-20th century, particle accelerators grew into enormous tools for probing the deep structure of matter. These machines could accelerate particles to high speeds and smash them together, creating conditions energetic enough for new particles to appear. In those collisions, matter and antimatter could be born together, fleeting but detectable. The antiproton was eventually discovered, confirming that antimatter was not limited to the electron's little mirror twin. Then came the antineutron, more subtle because it had no electric charge, yet still different from the neutron in its deeper properties. Piece by piece, the antimatter side of the particle world became more visible. It was not a single oddity. It was a general feature of nature. And this brings us back to the larger mystery. If matter and antimatter are such natural partners, why do we mostly see matter? Dirac's prediction helped reveal the mirror, but it did not explain why the mirror world is missing from the cosmos around us. The theory said antimatter could exist. Experiments proved that it does. Particle accelerators can make it. Cosmic rays can produce it. Radioactive atoms can emit it. Yet the galaxies we see appear to be made overwhelmingly of ordinary matter. There are no confirmed anti-stars shining in great anti-galaxies, at least not within the observable evidence we have. If they existed nearby, the boundaries where matter met antimatter would likely glow with signs of annihilation. The sky does not show that in the way it would need to, so antimatter arrived first as a triumph of theory and experiment, then immediately became a deeper question. The prediction answered one mystery and opened another. That too is common in science. A discovery rarely closes the book. More often, it turns the page and reveals that the book is much longer than expected. It's a bit like cleaning one drawer and realising the whole attic has been quietly waiting for attention since 1987. Dirac himself became associated with one of the great acts of theoretical prediction in modern physics. He did not find a positron by accident in a drawer. He did not set out to invent a science fiction fuel. He followed the demand that the electron be described correctly. He trusted the structure of the theory enough to take its strange implications seriously. And nature, through Anderson's cloud chamber, confirmed that the strange implication had substance. There is a lesson here about the way physics listens to the universe. Sometimes we listen with instruments, gathering data from telescopes, detectors, satellites, and experiments. Sometimes we listen with mathematics, asking what must be true if the rules we already know are to fit together. The best science lets these two forms of listening answer each other. Theory without experiment can drift too far into possibility. Experiment without theory can become a pile of facts without a map. But together they can do something extraordinary. They can reveal a particle before it is seen, then recognize it when it leaves a faint trail in vapour. The prediction of antimatter also reminds us that the small world is not built from intuition. No one looking at a table or a candle flame would naturally guess that the electron has a positively charged twin. Everyday life does not show us antimatter, because it cannot last among ordinary matter. The universe at our scale is calm because the antimatter that might have been around has mostly vanished or appears only briefly. To discover it, humanity had to push beyond everyday senses. We had to accept that the deeper world might have symmetries invisible to common experience. We had to let mathematics guide us towards something our eyes would never find on their own. And perhaps that is why this part of the story feels so special. Antimatter did not begin as a thing seen and then explained. It began as a thing required and then found. A shadow in an equation became a track in a chamber. A mathematical necessity became a particle. The invisible became visible, not because someone guessed wildly, but because the universe had left a clue in the way its laws fit together. As we continue, the story becomes more concrete. The positron, the antiproton, and the other antiparticles are not only ideas. They have behaviours, histories, uses, and dangers. They can be created in accelerators, born in cosmic collisions, and briefly held in traps. They can annihilate with ordinary matter, release energy, and give scientists precise signals to study. The mirror particles are real enough to measure, but delicate enough to vanish at a touch. And once we begin meeting them one by one, antimatter stops being a single mysterious word and becomes a whole hidden family of particles, each one reflecting the matter world in its own peculiar way. A particle can be strange in two different ways. It can be strange because it behaves unlike anything in ordinary life, which is already true for most of the quantum world. Or it can be strange because, according to the world we happen to live in, it almost feels as though it should not be here at all. Antimatter particles belong to that second kind of strangeness. They are real, measurable, and obedient to physical laws, but they appear in a universe that gives them almost no safe place to rest. They are like perfectly legitimate guests who arrive at a house where every chair, every wall, every cup, and every floorboard is made of something that destroys them the instant they touch it. It is not that they are impossible. It is that our corner of reality is deeply inconvenient for them. The first antimatter particle humanity truly met was the positron, the mirror partner of the electron. The electron is one of the quiet workers of the universe. It helps shape atoms, chemistry, electricity, magnetism, light, and the nervous activity that allows you to listen to these words, while perhaps wondering if your blanket is warm enough. Electrons are everywhere around us. They are in your skin, your tea, your phone, the air, the walls, the stars, and the dust slowly gathering in places you definitely cleaned recently. The positron is almost the same as the electron in mass, but its electric charge is reversed. It is like the electron reflected in a very strict cosmic mirror. Same weight, opposite sign, different fate. When the positron was discovered in cosmic rays, it confirmed that antimatter was not merely a mathematical curiosity. It was not a little mistake left behind by an equation that got carried away. It was out there, passing through detectors, leaving trails, behaving like a real particle because it was one. Imagine the feeling of seeing that track for the first time. A tiny path in a cloud chamber, curved the wrong way for an electron too light to be a proton, announcing that nature had made the very thing theory had dared to suggest. The positron was not loud. It did not arrive with a thunderclap or a headline written across the sky. It curved through vapour, a small pale signature of the universe saying, "Yes, the mirror exists." The positron is not rare in the way a lost treasure is rare. Nature can make positrons in several ways. Certain radioactive atoms produce them when they transform. High-energy events in space can create them. Cosmic rays can produce them when they strike other particles. Even powerful storms in Earth's atmosphere can be connected to bursts of high-energy activity where positrons may appear. This means that antimatter is not locked away only in giant laboratories. Tiny pieces of it are being made naturally, briefly, all the time. They do not last long in a world filled with electrons. A positron born into ordinary matter soon meets an electron, and when that happens, the two are converted into energy. The meeting is brief, precise, and final. Like two perfect opposites recognizing each other across a crowded room and immediately deciding to become light. This behaviour gives positrons a practical use that still feels slightly surreal. In medical imaging, positrons help doctors see inside the body. A special substance is introduced into the patient, chosen so that it gathers in certain tissues or organs. As it decays, it emits positrons. Those positrons travel only a short distance before meeting electrons. When they annihilate, they produce signals that detectors can capture. A computer then uses those signals to build images of what is happening inside the body. So the anti-electron, first predicted by a difficult theory and found in cosmic particles, became a tool for medicine. Somewhere in the quiet machinery of a hospital, antimatter is used not to destroy cities or fuel starships, but to help find disease. It is one of the best reminders that physics can be both cosmic and practical, both mysterious and useful, both the language of stars and the language of a scan room with slightly uncomfortable furniture. But the positron is only the beginning. The matter world does not consist only of electrons. At the centre of atoms we find protons and neutrons, and they too have antimatter partners. The antiproton is the antimatter counterpart of the proton. A proton carries positive electric charge. An antiproton carries negative electric charge. But the antiproton is not simply an electron in disguise. It is much heavier than an electron, just as the proton is. It mirrors the proton in mass while reversing its charge and deeper internal properties. If the positron is the electron's reflected twin, the antiproton is the proton's darker reflection, though darker only in metaphor. It does not glow with villainous intent. It is a particle following the rules it was given. Finding antiprotons was much harder than finding positrons. Positrons can appear in certain natural processes and are light enough to be produced more easily. Antiprotons require much more energy. To create them, scientists needed powerful particle accelerators, machines designed to push particles to high speeds and smash them into targets or other particles. In those collisions, energy can transform into new particle and antiparticle pairs. This is one of the strange gifts of high-energy physics. If you concentrate enough energy into a tiny region, nature may respond by making particles that were not there before, not from nothing, but from energy changing form. The particle world is less like a box of fixed marbles, and more like a deep field where enough disturbance can make new things rise briefly to the surface. The antiproton was finally detected in the middle of the 20th century, confirming that antimatter was not limited to the electron family. The discovery required careful measurement, because particle accelerators produce many kinds of debris. After a collision, detectors may see showers of particles, some familiar, some unstable, some moving quickly, some curving under magnetic fields. Scientists have to read those patterns with great care. They look at charge, mass, speed, curvature, and how particles interact. It is like trying to identify one rare bird in a storm of feathers, except the feathers are subatomic and most of them vanish before you have finished saying, well, that was interesting. The antiproton matters because protons are so central to ordinary matter. Every atom's nucleus contains protons. Change the number of protons, and you change the element. Hydrogen has one proton, carbon has more, oxygen has more still. The entire periodic table, with all its chemistry and personality, depends on protons. So the antiproton is not just another exotic particle, it is the antimatter version of one of the main building blocks of ordinary atoms. Once antiprotons were known, the possibility of antiatoms became more than a distant thought. If you have antiprotons and positrons, perhaps you can build antihydrogen, and if antihydrogen can exist, even briefly, then antimatter can form structures that resemble the atoms of matter. Then there is the antineutron, which is quieter in a different way. The neutron has no electric charge, so its antimatter partner does not announce itself through a simple charge reversal. An antineutron is neutral too. This makes it less obvious at first glance. If you're looking only for electric charge, the neutron and antineutron might both seem like silent guests standing in the corner, but they are not the same. Their internal properties are reversed. A neutron is made from quarks arranged in one way, while an antineutron is made from antiquarks arranged in the corresponding mirror way. The antineutron shows us that antimatter is not only about electric charge. Charge is the easiest reversal to explain, but the deeper story involves other quantum properties as well. That is important because it prevents us from oversimplifying antimatter. It is tempting to say that antimatter is just matter, with the electric charge flipped. For electrons and protons, that is a useful starting point, but it is not complete. Some particles are neutral, yet they still have antiparticles. The difference lies in deeper features, in the way particles participate in the full set of quantum rules. The universe has more labels than the ones that show up in ordinary electricity. It is as though matter carries several hidden signatures, and antimatter carries the mirrored versions of those signatures. Electric charge is the one we notice most easily because it pushes and pulls in familiar ways, but it is not the whole identity card. Once scientists had positrons and antiprotons, they could begin the delicate work of making antihydrogen. Ordinary hydrogen is the simplest atom, made from a proton and an electron. Antihydrogen is made from an antiproton and a positron. In principle, this sounds simple. Put one antiproton together with one positron, and there you are, antihydrogen, the mirror of the simplest atom in the universe. In practice, it is almost comically difficult. Antiprotons are hard to make. Positrons must be gathered. Both must be slowed down and cooled. They must be brought together without touching ordinary matter. The antiatoms must then be trapped, if possible, long enough to study. It is a bit like trying to assemble a tiny clock while wearing oven gloves, in a room where the floor eats the clock if you drop it. Antihydrogen is precious not because it is useful in large amounts, but because it lets us ask extremely deep questions. Does antihydrogen emit and absorb light in the same way as hydrogen? Does it have the same internal structure? Does gravity pull it downward as it pulls ordinary matter? If the laws of physics treat matter and antimatter with near-perfect symmetry, then antihydrogen should match hydrogen in very precise ways. If it does not, if even a tiny difference appears, that difference could point toward new physics. It could give us a clue about why the early universe ended up filled with matter instead of equal matter and antimatter. Studying antihydrogen is therefore like comparing a real object with its mirror image and looking for the smallest flaw in the glass. Most of the time, the mirror seems astonishingly faithful, but physicists are patient people when a mystery is large enough. They do not merely glance and say, close enough. They measure again. They improve the trap. They cool the particles more carefully. They refine the laser. They check the fall. They ask the same question with better instruments, because somewhere in a tiny disagreement might be the answer to why we exist at all. The phrase, particles that should not be here, is not meant to say that antimatter violates the laws of physics. It does not. Antimatter belongs. The strange part is that it belongs to a universe where it is nearly absent. Every antiparticle we create or detect appears like a reminder of a lost balance. The laws allow it, but the history of the cosmos removed most of it. So when a positron appears in a detector, or an antiproton is made in an accelerator, it feels like a message from the early universe, from a time when matter and antimatter were closer to equal partners. Each antiparticle is a small surviving echo of what the universe could have been. If large amounts of antimatter existed nearby, we would expect to see signs. Matter and antimatter meeting in space would produce energetic radiation. At the borders between matter regions and antimatter regions, annihilation would be hard to hide. Astronomers look for such signals because the question is important. Could there be anti-stars somewhere far away? Could entire anti-galaxies exist beyond what we can easily detect? The evidence so far suggests that the observable universe is overwhelmingly made of matter. That does not mean no antiparticles exist. They certainly do. But it does mean the grand structures of the cosmos, the galaxies and clusters we see, appear to share our matter identity. The universe, at least the part we can study, chose one side. This makes every laboratory-made antiparticle feel a little artificial and a little ancient at the same time. Artificial because we create it with machines, by forcing particles into high-energy collisions. Ancient because the process echoes conditions from the early universe, when energy and particles were constantly transforming into one another. Particle accelerators are sometimes described as microscopes, because they help us probe small distances. But they are also, in a limited way, time machines. Not because they send us into the past, but because they recreate tiny fragments of the high-energy behaviour that filled the universe when it was young. When an antiproton appears in a modern detector, it is a particle made now, but the rules that allow it belong to the universe's earlier story. Charged antiparticles can be guided by magnetic fields, and this is one of the reasons we can study them at all. A magnetic field bends the path of a charged particle. If the charge is opposite, the bending direction is opposite. This lets scientists separate matter from antimatter, identify particles, and hold them in carefully designed traps. A positron curves one way where an electron would curve another. An antiproton responds oppositely to a proton. This behaviour gives detectors their language. Curves become evidence. Trails become identities. The invisible becomes legible. There is a gentle irony here. Antimatter has such a dramatic reputation, yet our knowledge of it often comes from delicate curves, faint flashes, and careful timing. The universe does not usually label its particles for our convenience. It does not send a note saying, "Congratulations, you have found an antiproton." Scientists infer, they reconstruct, they compare. They build machines that turn tiny events into readable traces. In this sense, particle physics is partly the art of learning from what vanishes. Many particles live only briefly. Many antiparticles annihilate quickly. But before they go, they leave patterns, and those patterns can be enough. The antimuon, the anti-tau, antiquarks, and other antimatter partners belong to the same expanding family. Every charged lepton has its antiparticle. Quarks have antiquarks. The particles inside protons and neutrons have mirror counterparts too. The more deeply physicists explored, the more antimatter appeared not as an exception, but as part of the architecture. Matter and antimatter are woven together in the theory, even if they are not equally present in the cosmos today. The particle zoo, as physicists sometimes call it, is not merely a jumble of strange creatures. It has relationships, symmetries, and pairings. Antimatter is one of the patterns that gives the zoo its hidden order, though the animals are still not always well behaved. What makes all this even more remarkable is that antimatter particles are not weaker or less real than matter particles. A positron is not a ghost of an electron. An antiproton is not a second-class proton. If you had a region of space containing only antimatter, and if no ordinary matter touched it, antimatter could in principle form anti-atoms, anti-chemistry, and perhaps larger structures. The laws do not forbid an anti-world. The obstacle is contact with our matter world, and the historical fact that the universe did not leave much antimatter around. From the antimatter point of view, if such a point of view could exist, we would be the dangerous opposite. A creature made of antimatter would find our ordinary matter just as destructive as we find theirs. The danger is mutual. The label depends on who is speaking. That thought helps remove some of the mythology. Antimatter is not evil matter. It is not matter's enemy in a moral sense. It is the partner that cannot coexist with matter in the same place without transformation. It is a reminder that opposites are not always good and bad. Sometimes they are simply two halves of a deeper rule, unable to touch because their meeting releases what they are into something else. The particles that should not be here then are here because the universe still knows how to make them. It makes them in radioactive decay, in cosmic collisions, in lightning-related high-energy events, and in the giant machines built by human curiosity. They appear briefly, carrying the signatures of the mirror world. We catch them, guide them, measure them, sometimes use them, and often lose them almost immediately. They are temporary visitors in a matter-dominated universe, and each one carries the same quiet question. If matter and antimatter are both allowed, why did one become the world and the other become a trace? As we follow that question forward, we come to the moment where matter and antimatter meet. Not as a metaphor, not as a mirror held at a distance, but as an actual encounter between particle and antiparticle. It is there, in the instant of annihilation, that antimatter earns much of its strange reputation. The meeting of opposites becomes light, energy, and sometimes new particles. The substance of both is transformed, and the universe reveals just how much power is hidden inside even the smallest pieces of matter. When people first hear that matter and antimatter destroy each other on contact, the mind naturally reaches for the loudest possible images: a flash brighter than the sun, a laboratory shaking, a metal door bending outward, someone in a white coat saying, "Rather too late. Perhaps we should have used the larger containment field. Science fiction has trained us well." Antimatter has become one of those words that seems to arrive already wearing dramatic lighting. But the real process, while powerful, is also precise, quiet at the scale where it begins, and deeply orderly. It is not chaos, it is transformation. Annihilation sounds like disappearance, as though matter and antimatter simply meet, and both fall out of existence. But physics does not allow such casual vanishing. The universe is mysterious, yes, but it is not sloppy. When a particle meets its antiparticle, what they were becomes something else. Their mass, their energy, their motion, their identities, all have to be accounted for. Often the result is light, or other particles, or a burst of energy carried away in forms that detectors can measure. Nothing is truly rubbed out of the cosmic ledger. It is more like two notes struck together that stop being separate sounds and become a new chord. The simplest example is the meeting of an electron and a positron. The electron is ordinary matter. The positron is its antimatter partner. They have the same mass but opposite electric charge. When they encounter each other under the right conditions, they can annihilate and produce energetic light. That light carries away the energy that once belonged to the pair. The particles are gone as particles, but not gone as existence. They have changed their form. The universe has taken two tiny opposites and translated them into radiation. There is a strange elegance in that. A meeting that sounds violent is, at the deepest level, balanced. The electron does not win. The positron does not win. The two are not smashed into dust in the ordinary sense. They convert. They become a different expression of the same underlying energy. It's a bit like two people arguing so perfectly that they cancel the argument and accidentally write a song. Perhaps not the usual outcome in real life, but the particle world has its own manners. With heavier particles, such as protons and antiprotons, the process becomes messier. A proton is not a simple dot. It is a composite particle, made from quarks held together by the strong force. An antiproton is made from antiquarks. When a proton and antiproton meet, their internal ingredients can annihilate and rearrange into other particles before those particles decay further. The result may be a little cascade of products, a short-lived burst of particle activity. It is still governed by conservation laws, still accountable, still not magic. But it is less like a clean bell tone, and more like dropping a tray of cutlery in a very tiny kitchen. This is why antimatter has such a powerful reputation as an energy source. When matter and antimatter annihilate, a large fraction of their mass can become usable energy. Compared with chemical reactions like burning fuel, the amount of energy locked in matter is enormous. Chemical energy comes from rearranging electrons around atoms. Nuclear energy comes from changing atomic nuclei. Matter-antimatter annihilation goes deeper. It can transform the particle and antiparticle themselves into energy and other particles. That sounds like the ultimate fuel, and in a purely physical sense it is extraordinary energy dense. But there is a very large difference between a beautiful physical idea and a practical engine. Antimatter is not something we can mine from a hillside or scoop from space with a bucket, however satisfying that bucket would be in a science fiction painting. We make antimatter in tiny amounts, usually by spending far more energy than we get back. Particle accelerators can produce antiparticles, but they are not antimatter factories in the everyday sense. They are research instruments, built to probe nature, not to fuel a fleet of starships. The amount of antimatter humans have made is incredibly small, and storing it is difficult because it must not touch ordinary matter. The fuel tank would also have to be a trap, and the trap would have to be almost impossibly careful. Still, the idea of antimatter energy is not foolish. It is physically real. The problem is scale, cost, storage, and control. These are not small problems like forgetting where you put your keys. They are enormous problems, like discovering your keys are inside a volcano and also made of lightning. The particles must be created, slowed, collected, contained, and then released in a controlled way. Any container made of ordinary matter cannot simply hold antimatter against its walls. Charged antiparticles must be suspended by electromagnetic fields. Neutral antimatter atoms require even subtler traps. The engineering challenge is not just hard, it is almost comically unforgiving. This brings us to one of the most important things to understand about annihilation. The danger is not that antimatter is unstable by itself. A positron drifting in empty space does not explode from loneliness. An antiproton does not wake up one morning and decide to be dramatic. Antimatter can persist if it is kept away from matter. The danger comes from contact. Our world is made of matter, so contact is very easy. The air is matter. Dust is matter. The walls are matter. A fingertip is matter. Even the best vacuum chamber still has to be built from matter, and that is why fields are used to keep antimatter away from the physical surfaces around it. In the particle world, contact does not require touching in the familiar sense of two marbles bumping together. Particles interact through fields and quantum processes. Their encounter is not a tiny collision of hard balls, it is a meeting of identities allowed by the rules of physics. When a particle and its antiparticle can transform into other permitted forms, they do. The result depends on the particle type, the energy involved and the conditions of the encounter. But the basic idea remains simple enough for a quiet evening. Matter and antimatter are mirror partners, and when the right partners meet, their separate particle identities can end. There is something almost poetic in that, though we should not get too misty about it. Annihilation is not romance, it is physics. But it does show us that the universe is not built from permanent little beads. Particles can appear, disappear as particles, transform, decay, merge into energy, and emerge in other forms. At ordinary human scales, objects seem solid and stable. A chair remains a chair unless someone sits on it with unfortunate enthusiasm. A cup stays a cup until gravity becomes involved. But at the deepest level, matter is more flexible than it looks. The universe is not a warehouse of unchanging pieces. It is a set of processes, transformations, and conserved quantities moving through different forms. This is one reason particle detectors are so important. Scientists often cannot see the original annihilation directly in a simple visual way. Instead, they see what comes out of it. Light hits detectors, particles leave tracks, energy is deposited in layers of instrumentation. Computers reconstruct the event. From the pattern of traces, physicists infer what happened. It is a bit like walking into a kitchen after someone has made an ambitious cake, and working backward from the flour on the counter, the eggshells in the sink, and the suspiciously happy dog. The original event is gone, but its evidence remains. In medical imaging, this evidence becomes useful. Positrons produced inside the body quickly meet electrons. Their annihilation produces pairs of energetic light signals travelling in opposite directions. Detectors surrounding the patient catch those signals, and computers use them to build a picture of where the positrons were emitted. This technique does not require large amounts of antimatter. It relies on tiny, carefully controlled processes. The body is not filled with dangerous anti-stuff in the way the word antimatter might make one imagine. The positrons appear, travel a very short distance, annihilate, and leave information behind. It is delicate, controlled, and useful. A cosmic principle turned into a medical map. There is something deeply satisfying about that. The same process that reveals the raw conversion of matter and antimatter can also help doctors understand living tissue. The universe's dramatic mirror particles become part of a diagnostic tool. It is as though nature's most theatrical idea took a part-time job in healthcare. And in that quieter role, annihilation is not a disaster, it is a signal. In astronomy, annihilation can also become a signal. If large amounts of antimatter existed in contact with matter somewhere in space, we would expect to see radiation from the boundary where the two met. This is one reason scientists doubt that there are nearby antimatter galaxies mixed among ordinary ones. If an anti-galaxy were surrounded by matter, or if anti-gas clouds met matter-gas clouds, the contact regions would glow in ways we should notice. The sky is not full of those signs. That does not mean no antiparticles exist in space. They do. Cosmic rays include antimatter particles, and energetic astrophysical processes can create them. But entire large structures made of antimatter would be hard to hide if they were close enough and interacting with matter. The absence of widespread annihilation signals is part of the mystery. Antimatter exists. We know how to make it. Nature makes it. Yet the universe is not half matter and half antimatter in any obvious patchwork. It is overwhelmingly matter, at least across the regions we can observe. So annihilation tells us not only what happens when opposites meet, but also what must not be happening everywhere. If the early universe created matter and antimatter in equal amounts, then most of those pairs should have annihilated. And they did, as far as we understand. But a tiny excess of matter remained. That leftover is everything. The galaxies are leftovers. The stars are leftovers. The ground beneath you is a leftover. Your hands, your thoughts, your memories, and the sleepy pressure behind your eyes are all made from the tiny surplus that did not find an antimatter partner. That thought can make the familiar world feel fragile. It can also make it feel miraculous, though not in a supernatural sense. Miraculous, as in highly unlikely from our everyday point of view, and yet undeniably here. A perfect balance would have left almost no matter. A slight imbalance gave us a universe full of structure. The violence of annihilation cleared away most of the original particle pairs, and the quiet residue became the matter world. Creation, in this sense, was not only the making of particles, it was also the survival of an imbalance after destruction had done its work. The word annihilation therefore carries two meanings in the story of antimatter. In the laboratory, it describes a specific particle process. A particle meets its antiparticle and transforms into other energy forms. In cosmology, it describes a vast early episode in which matter and antimatter pairs disappeared into radiation, leaving only a small matter excess behind. The first is tiny and measurable. The second shaped the entire visible universe. The same principle, scaled from the smallest interactions to the largest consequence. It is worth taking a breath with that. The atoms in your body did not survive because matter was vastly more powerful than antimatter. Matter did not win in a grand battle because it was stronger, brighter, or more deserving. The difference seems to have been subtle. Very subtle. A tiny tilt in the rules, a slight preference in certain processes, a delicate asymmetry. We still do not fully understand it. But we know it must have happened, because otherwise there would be no ordinary matter left to ask the question. This is why annihilation is not merely destructive in the story of the universe. It is part of the reason the universe became transparent, radiant, and later structured. When matter and antimatter annihilated in the early cosmos, they produced radiation. The universe was filled with energy, light, and particles interacting in a hot, dense sea. As it expanded and cooled, the leftover matter began the long journey toward atoms, stars, galaxies, and chemistry. Annihilation removed the balanced pairs, and the imbalance supplied the building material. Destruction and creation were not opposites here. They were stages in the same unfolding. On a human scale, we're used to destruction meaning loss. A broken glass is no longer useful as a glass. A burned piece of paper no longer carries its writing. But in physics, destruction often means transformation. The glass becomes shards, heat, sound, and scattered motion. The paper becomes ash, gas, heat, and light. Matter and antimatter annihilation is transformation in a more fundamental key. The particles themselves cease to be those particles, but what they carried is preserved in the products. The universe changes its vocabulary, but not its total meaning. This helps calm some of the fear around antimatter. Yes, annihilation can release enormous energy if enough matter and antimatter meet. Yes, it is powerful, but it is not supernatural. It follows rules. It can be measured, predicted, and used in tiny controlled ways. The terror often comes from imagining large quantities, and large quantities are precisely what we do not have. The universe may have produced immense amounts in its earliest moments, but today, in laboratories, antimatter exists in traces. Its power is real, but our ability to gather it is extraordinarily limited. The quiet violence of annihilation is therefore not a movie explosion first. It is a window. It lets us see that mass and energy are interchangeable forms of one deeper accounting. It lets us detect antimatter through the signals it leaves behind. It helps medicine image the living body. It helps astronomers search for hidden antimatter regions. And it points backward to the early universe, where almost all matter and antimatter met and transformed, leaving behind the small excess that became us. So when we picture matter meeting antimatter, perhaps the best image is not a bomb, but a brief flash of translation. Two mirror particles approach, their separate identities end. Light or new particles carry the story away. The detector listens, the scientist reads the trace, the universe balances its books. On the smallest scale, it may happen in less time than the mind can hold. On the largest scale, its consequences have lasted for billions of years. And once we understand that matter and antimatter destroy each other so efficiently, the next mystery becomes impossible to avoid. If the young universe was full of both, and if their meeting turns them into radiation, why is anything still here? Why did the early cosmos not become a smooth bath of light with no atoms, no stars, no planets, and no listeners? Somewhere in the first moments, A small unfairness entered the story, and physics has been trying to understand that unfairness ever since. If matter and antimatter destroy each other so efficiently, then the most surprising thing about the universe is not that antimatter exists. It is that anything exists at all. The stars should not be here. The planets should not be here. The quiet dust on your shelf, the oxygen in your lungs, the bones in your hand, the sleepy little thoughts drifting through your mind right now, none of it should have had much chance if the earliest universe had been perfectly balanced. Matter and antimatter were both allowed by the laws of physics. They could appear together, they could meet again, and when they met they could transform back into energy. A clean, elegant, almost ruthless exchange. So the question is simple enough to say, but deep enough to keep physicists busy for generations. Why did the universe not erase itself in its first moments? To picture the problem, we have to drift far backward, beyond Earth, beyond the sun, beyond the first stars, beyond even the first atoms. Not backward into a dark, empty space, but into a universe so hot and dense that the familiar forms of matter had not yet settled down. There were no galaxies, no planets, no chemistry, no quiet corners. The early universe was not a place in the everyday sense because space itself was still expanding and cooling from an extreme beginning. It was more like a storm of energy and particles, a cosmic furnace where the ingredients of reality were still changing form. In that early heat, energy could become particles and particles could become energy. Matter and antimatter could be made in pairs. A particle and its antiparticle could appear from concentrated energy, move briefly through the young universe, and then meet again and annihilate. This happened not once or twice, but on a scale beyond ordinary imagination. The newborn cosmos was filled with these transformations, a restless exchange between energy, matter, antimatter, and radiation. If you could somehow watch it, which you absolutely could not because you would be less than vapor in less than an instant, it would not look like a calm beginning. It would be a universe still deciding how to become itself. The strange part is that matter and antimatter seem to have been created in nearly equal amounts. Nearly is the word that matters. If they had been exactly equal, then almost every matter particle would have found an antimatter partner. They would have annihilated, leaving behind a universe filled mostly with radiation. There might still have been light, but almost no matter to build stars or planets. No atoms to gather into clouds, no carbon, no water, no living things, no one waiting for the kettle to boil while having an existential crisis about particle physics. A perfectly balanced universe would have been, in a sense, too perfect to become interesting. But the universe we see is not like that. It is full of matter. Not full in the sense that space is crowded, because space is astonishingly empty, but full in the sense that the structures we see are made from matter. Galaxies are matter, stars are matter, gas clouds are matter, dust grains are matter. The Earth is matter. You are matter. We do not see equal amounts of antimatter arranged into anti-galaxies all around us. We do not see the sky glowing everywhere, with the signals we would expect from large matter and antimatter regions colliding at their borders. Antimatter exists in tiny amounts and special conditions, but the visible universe is overwhelmingly made of ordinary matter, so something must have happened. Somewhere in the early universe, matter gained the tiniest advantage. Not a dramatic victory. Not a grand battle where matter charged forward wearing a tiny helmet. More like a whisper of imbalance. For every enormous number of matter and antimatter particles that destroyed one another, a very small excess of matter remained. That excess, almost nothing compared with the original storm, became everything. It became hydrogen. It became stars. It became galaxies. It became the long chain of cosmic chemistry that eventually made planets, oceans, cells, forests, animals, and the listener quietly hearing this sentence. This is one of those ideas that can make the room feel different for a moment. The matter around you is not the main crowd from the beginning. It is the leftover, the survivor, the small surplus after the great cancellation. The universe did not avoid annihilation entirely. Most of the original matter and antimatter may have annihilated. What remained was only the slight extra matter that had no antimatter partner left to meet. Everything solid and familiar is made from that ancient remainder, and that is both beautiful and deeply puzzling. We can tell that there was an imbalance because we are here. The evidence is not hidden only in a detector or a distant telescope. The evidence is the existence of matter itself, but knowing that an imbalance happened is not the same as knowing why. That is the heart of the problem. What rule, process, or hidden difference allowed matter to outlast antimatter? Physicists have a name for the general question of how the matter excess formed. It is often called the origin of matter, or more technically, the process by which the universe came to contain more matter than antimatter. But naming a mystery is not the same as solving it. It is a bit like labelling a cupboard mysterious cupboard, and then pretending the job is done. The real challenge is to understand what physical processes in the early universe could have created that tiny surplus. One important clue is that the laws of physics must treat matter and antimatter almost the same, but not exactly the same. If the treatment were perfectly equal in every relevant way, then it would be very difficult to explain how one side gained an advantage. The mirror would be too perfect. But experiments have shown that nature does allow some tiny differences between the behaviour of certain particles and their antiparticles. These differences are subtle. They do not mean antimatter falls upward or behaves like a magical substance. They mean that in some rare particle processes the mirror is not perfectly faithful. This kind of tiny asymmetry is one of the most important discoveries in modern particle physics. It showed that matter and antimatter are not always treated as exact equals by every process in nature. The difference is small, but small differences can matter enormously when the universe is young, hot, dense, and changing very fast. A tiny bias repeated across vast numbers of particle interactions could help tilt the cosmic balance. The trouble is that the differences we have measured so far do not seem large enough by themselves to explain all the matter in the universe. The crack in the mirror is real, but it may not be wide enough. That suggests that there may be more physics still hidden from us, and that is where antimatter becomes a doorway to new questions. It is not just that we want to know what antimatter is. We want to know whether its behaviour contains a clue to missing laws. Perhaps there were particles in the early universe that we have not yet discovered. Perhaps there were interactions that happened only at energies far beyond what our machines can easily reach. Perhaps neutrinos, those ghostly particles that pass through matter with almost no interest in stopping for a chat, played a role. Perhaps there is some deeper imbalance connected to forces or fields we have not fully understood. The early universe may have used ingredients we are still trying to identify. There are broad conditions that any successful explanation has to satisfy. The universe must have been able to create processes that do not preserve the number of matter particles in a simple, balanced way. It must have included some difference between matter and antimatter behaviour, and it must have been out of perfect thermal balance, because a universe in complete equilibrium tends to wash away attempts at building an imbalance. These are not the full solution, but they are like clues pinned to a board. They tell physicists what kind of story could work, even if the exact story is still missing. One gentle way to imagine it is to picture a huge dance floor filled with paired dancers, one matter, one antimatter. If every pair moves perfectly symmetrically, and every dance ends with both partners leaving together, the hall empties. But if, in the tiniest fraction of dances, one matter dancer is left standing without a partner, and if this happens again and again across a huge enough crowd, then after the great leaving, a small group remains. That group may seem insignificant compared with the original crowd, but if everyone else has gone, the leftover group becomes the whole visible party. The galaxies are that leftover group, rather a successful after-party, considering the circumstances. Of course, the real early universe was not a ballroom. It was unimaginably hot, expanding, and filled with quantum fields and particle interactions. But the basic point remains. A very small bias can have enormous consequences if the scale is large enough. The difference between a universe with matter and a universe with almost no matter may have been extraordinarily tiny at the beginning. In ordinary life, such a tiny imbalance might seem unimportant. If you spill one extra grain of sugar on the counter, you do not usually rewrite the fate of reality, unless perhaps you're making a very exact recipe and a judge is watching. But in the early universe, tiny differences could be amplified by the sheer number of particles involved. This also means that the universe may owe its existence as a structured place to imperfection. Perfect symmetry would have been elegant, but sterile. A flawless balance between matter and antimatter might have left no atoms. The slight failure of balance gave the cosmos something to work with. Stars needed matter, planets needed matter, chemistry needed matter, life needed matter. In that sense, the universe became rich because the mirror was not exact. There is a quiet lesson in that, though we should not turn physics into a greeting card too quickly. The point is not that all imperfections are secretly wonderful, especially when one is trying to assemble furniture from unclear instructions. But in this particular case, a tiny physical asymmetry may be the reason there is any furniture at all. The matter world is a monument to a small early imbalance. Every mountain and moon is a kind of fossil of that difference. Scientists search for answers in many ways. Particle accelerators recreate high-energy collisions, not the Big Bang itself, but tiny controlled events where matter, antimatter, and new particles can appear. Detectors study how particles decay, how often certain outcomes happen, and whether matter and antimatter versions behave with measurable differences. Experiments with antimatter atoms compare their properties with ordinary atoms. Neutrino experiments look for clues in particles that barely interact, but may hold deep secrets about the early universe. Cosmologists study the radiation left over from the young universe, the distribution of galaxies, and the history of cosmic expansion. Each approach is a different way of asking the same question: what made matter stay? So far, the answer remains incomplete. That is not a failure, it is a frontier. Physics has already learned enough to know that the question is real, precise, and profound. We know antimatter exists. We know matter and antimatter can annihilate. We know the universe contains far more matter than antimatter. We know certain symmetries are not perfect. We know the known differences are probably not enough. That is a very particular kind of ignorance, the useful kind. It is not blank confusion. It is a map with a bright unfinished region at the edge. The mystery also connects the smallest particles to the largest structures. This is one of the pleasures of physics. A tiny difference in particle behavior can shape the fate of galaxies. A process too small to see directly with the eye can decide whether stars will ever form. The matter in a single fingertip and the matter in a distant spiral galaxy share the same ancient origin. Both are made from the surviving excess. Both are part of the answer, even if the answer is not yet complete. It is worth pausing on the emotional strangeness of this. We often think of the universe as vast, cold, and indifferent, and in many ways it is. Yet its existence as a place with structure depends on a delicate imbalance. The cosmos is not just big, it is oddly specific. Had the early conditions been a little different, had the laws treated matter and antimatter with perfect equality in every relevant process, the story might have ended before atoms began. Instead, the imbalance remained. The universe cooled. The leftover matter gathered. Gravity began its slow work. Simple atoms formed. Stars ignited. Heavier elements were forged. Planets assembled. And much later, on at least one small world, matter became awake enough to wonder why it was not cancelled. There is a kind of loop in that thought. Matter survived. eventually built minds, and those minds now investigate the survival of matter. The universe left a question inside its own leftovers, and we, being made of those leftovers, are asking it back. Antimatter therefore teaches us that absence can be as important as presence. The antimatter that is mostly not here tells us something. If we saw equal antimatter everywhere, the universe would look different. If all antimatter had perfectly cancelled matter, there would be no observers. The missing antimatter is not just missing. It is a clue shaped like an absence. Like a chair pulled away from a table, it tells you someone was expected, or someone has gone. This is why the study of antimatter has never been only about danger or energy. It is about origin. The question is not simply what happens if matter and antimatter meet, but why they did not leave the universe empty when they did. Why was there a small remainder? What deep rule allowed that remainder to be matter? Why do the laws of physics contain a mirror, and why did the mirror not reflect the cosmos equally? As we follow antimatter from the early universe into the modern world, the scale changes, but the mystery remains close. The same positrons that help reveal processes inside the body are part of the same antimatter family that points back to the first moments. The same antiprotons trapped in laboratories belong to the mirror side that mostly vanished from the cosmos. The same annihilation that could have left nothing behind now helps detectors see, measure, and understand. Antimatter is not only a lost twin from the beginning. It is still being made, still being used, still being held carefully away from the matter walls of our instruments, as we keep asking what its brief presence can tell us about the universe that survived. Antimatter may have begun for us as a prediction in a physicist's equation and a delicate curve inside a cloud chamber, but it did not stay there. It moved in the slow and patient way scientific ideas often do, from theory into instruments, from instruments into laboratories, from laboratories into hospitals, and from the edge of particle physics into the wider universe. That is one of the surprising things about antimatter. It sounds like the kind of concept that should remain locked inside the deepest rooms of physics, surrounded by warning signs and people who speak very quietly near important machinery. Yet traces of it are used in medicine. It appears naturally in space. It flickers into existence in the atmosphere above our heads. And in a few extraordinary laboratories, it is held, for brief careful moments, inside machines designed to keep it from touching the matter world around it. This is where antimatter becomes both more familiar and more unbelievable at the same time. More familiar because we begin to see that it is not only a cosmic riddle from the beginning of time. It has practical uses. It can help doctors look inside the human body. It can help astronomers understand high-energy events in space. It can be made, guided, measured, slowed, and trapped. But it becomes more unbelievable because every one of these uses depends on handling something that cannot safely touch the ordinary material from which all our tools are made. We study the mirror using equipment built from the thing the mirror destroys. Let us begin in the hospital, which may seem like an unlikely place to meet antimatter. Hospitals belong to the world of clipped footsteps, soft conversations, waiting rooms, pale lights, and machines that hum with a seriousness all their own. They are not the first place most people imagine when they hear the word antimatter. We tend to picture a starship, a secret laboratory, perhaps a glowing orb held in a magnetic bottle by a scientist with slightly tired eyes. But one of the most important everyday uses of antimatter is found in medical imaging, in a technique known as positron emission tomography. The positron, as we have seen, is the antimatter partner of the electron. It has the same mass as an electron, but the opposite electric charge. In certain types of radioactive decay, positrons are emitted naturally. Medicine takes advantage of this. A patient is given a substance containing atoms that release positrons. That substance is chosen because it travels through the body in a useful way, often gathering in tissues where doctors want information. The positrons do not travel far. The body is full of electrons because the body is made of ordinary matter. So a positron soon meets an electron. When they meet, they annihilate, producing energetic light that travels outward in opposite directions. Detectors arranged around the patient catch these signals. The computer then reconstructs where the signals came from, building a picture of activity inside the body. It is not simply a photograph of shape. It can show function. It can reveal where certain processes are happening more actively. This is especially useful in studying cancers, brain activity, heart conditions, and other medical questions where chemistry and metabolism matter. In this quiet way, antimatter becomes a messenger. It appears for an instant, meets matter, transforms into light, and that light carries information outward. There is something remarkable in that. The same basic process that sounds so dramatic in discussions of Starship fuel is used calmly in hospitals to help doctors see what the eye cannot. Antimatter does not arrive there as a great destructive force. It arrives in tiny, controlled, useful traces. It does its brief work and vanishes. It is like a candle flare in a dark room, not burning the house down, but revealing where the furniture is. Though perhaps, given that this is medical imaging, the furniture is made of organs and tissues, which is rather less cozy as a metaphor but much more helpful to medicine. This medical use also teaches us something important about scale. Antimatter's reputation comes from how much energy could be released if large amounts met ordinary matter. But in hospitals, the amounts are incredibly small. The process is controlled. The positrons are not roaming freely in a dangerous cloud. They appear from radioactive decay, travel a short distance, annihilate with electrons, and produce signals. The danger is managed not by treating antimatter as magic, but by understanding exactly how it behaves. This is often the difference between fear and technology. A thing that sounds terrifying becomes useful when its rules are known well enough. Outside the hospital, antimatter also appears in nature. Space is not empty in the simple sense. It is full of particles, radiation, magnetic fields, cosmic rays, and violent events that can accelerate matter to extraordinary energies. Cosmic rays, which are high-energy particles travelling through space, can strike atoms in Earth's atmosphere and produce showers of secondary particles. Among these can be antimatter particles, including positrons and antiprotons. In other words, particles from deep space can hit the upper atmosphere and create brief fragments of the mirror world above our heads. Antimatter is not only something humans make. Nature has been making small amounts of it all along. The sun can produce antimatter-related particles during energetic events. Exploding stars and other violent astrophysical environments can create conditions where particle and antiparticle pairs appear. Near black holes, neutron stars, and regions with intense magnetic fields, nature can accelerate particles so violently that new particles are born from energy. Space is full of engines far more powerful than anything humans have built. When we detect antimatter in cosmic rays or from high-energy regions, we are seeing traces of those engines at work. Astronomers study these traces carefully because antimatter in space can tell us about extreme processes. A positron signal from the galaxy, for example, raises questions about where those positrons came from. Were they produced by radioactive elements made in stars? Were they created near compact objects? Were they linked to energetic events in the centre of the galaxy? Each possibility tells a different story about what is happening in places we cannot visit. Antimatter becomes a clue carried across space, a tiny signature of violence, heat, and acceleration in distant regions. There is even antimatter connected to Earth itself in unexpected ways. Powerful thunderstorms can produce bursts of high-energy radiation, and under certain conditions these events can create positrons. That means a storm cloud, the kind you might watch from a window while rain taps the glass, can briefly participate in the same particle story as cosmic rays and accelerators. Lightning is already dramatic enough, of course. It hardly needed an antimatter subplot. but nature rarely asks whether a topic has enough drama before adding more. These natural appearances of antimatter are brief. They do not build anti-mountains in the sky or anti-oceans in space. They appear as particles and signals, as products of high-energy processes. The larger mystery remains. We do not see great regions of antimatter in the visible universe. If antimatter stars or antimatter galaxies were common nearby, their contact with ordinary matter at boundaries would likely produce detectable radiation. The sky, as far as evidence tells us, is overwhelmingly a matter sky. The antimatter we find in space is more like sparks than landscapes. In laboratories, the situation is different again. Here, humans create antimatter deliberately. Particle accelerators can produce antiparticles by smashing particles together at high energies. The energy of the collision can become new particle and antiparticle pairs. But making antimatter is not like filling a tank. It is more like producing a few rare notes from an enormous machine and then trying to catch them before they fade. The amounts are tiny. The energy cost is enormous compared with the energy that could be recovered. The point is not mass production. The point is understanding. Once antimatter particles are created, scientists face the challenge of handling them. Since ordinary matter would annihilate with antimatter, the particles cannot simply be placed in a physical container. Charged particles, like positrons and antiprotons, can be held using electric and magnetic fields. These fields act like invisible hands, guiding the particles and keeping them away from material walls. The particles move inside carefully designed traps, often in extreme vacuum and at very low temperatures, where unwanted collisions are minimized. The entire system has to be patient, precise, and unforgiving. A trap for charged particles can use combinations of electric and magnetic fields to confine them. The idea is not to build a tiny cage made of metal bars, because metal bars are matter, and matter is exactly what antimatter must avoid. The cage is made of fields. The walls are not physical surfaces, but forces. The particles are suspended, steered, slowed, and cooled. It is a delicate arrangement, like trying to keep a moth floating in the centre of a room using only moving air, except the moth is an antiproton, and the walls would turn it into energy if it touched them. Creating antihydrogen is even more difficult and even more fascinating. Antihydrogen is the antimatter version of hydrogen. Ordinary hydrogen is made from one proton and one electron. Antihydrogen is made from one antiproton and one positron. To create it, scientists bring antiprotons and positrons together under carefully controlled conditions. If they combine, an antiatom forms. But antihydrogen is electrically neutral overall, which makes it harder to trap using electric fields alone. Scientists use magnetic properties and very carefully shaped magnetic fields to hold these antiatoms long enough to study them. Why go to so much trouble for a few antiatoms? Because antihydrogen lets us compare matter and antimatter with extraordinary precision. Hydrogen is the simplest atom and one of the best understood systems in physics. Its light has been studied with remarkable accuracy. If antihydrogen behaves exactly like hydrogen, that supports the idea that matter and antimatter obey the same laws in the expected way. If it differs even slightly, that difference could be a clue to physics beyond what we currently understand. So every trapped antiatom is not merely a trophy, it is a question in physical form. Scientists want to know whether antihydrogen absorbs and emits light in exactly the same patterns as hydrogen. They want to know whether antimatter responds to gravity just like matter. For a long time, people wondered whether antimatter might fall differently. Most physicists expected it to fall downward like ordinary matter, but expectation is not measurement. Recent experiments have begun directly testing how antihydrogen behaves under Earth's gravity, and the results support the view that antimatter falls downward. Still, the work continues because greater precision matters. The question is not only whether it falls, but whether it falls in exactly the way our theories predict. There is something almost tender about these experiments. Not tender in the emotional sense, perhaps, though one can become fond of a well-behaved anti-atom after working that hard to make it. tender in the sense of careful, fragile, exact. These are experiments where tiny signals matter, where particles must be cooled and trapped, where stray gas atoms can ruin the event, where a handful of anti-atoms can carry information about the deepest symmetries of nature. It is science done with immense machinery and delicate patience at the same time. The machines that hold antimatter are not built only to prevent destruction, they are built to create time for questions. An antiparticle that annihilates instantly tells us only that it touched matter. An antiparticle held for a little while can be measured. An antiatom trapped long enough can be illuminated with lasers, watched as it moves, compared with its matter counterpart. The trap turns a fleeting visitor into a subject of study. It gives the mirror time to answer. And the answers so far are fascinatingly ordinary. Antimatter behaves very much as expected. Positrons behave like anti-electrons. Antiprotons behave like mirror protons. Antihydrogen resembles hydrogen in the ways measured. Gravity appears to pull antimatter downward. That might sound almost disappointing, as though the universe has declined to perform a trick. But in physics, confirming a deep symmetry is not dull. It is profound. And if tiny differences eventually appear, they will be all the more meaningful because the tests were so careful. One should also remember that antimatter research is connected to many practical technologies beyond the antiparticles themselves. The machines built to produce, trap, cool and detect antimatter require advances in accelerator physics, vacuum systems, magnets, cryogenics, detectors, computing, and precision measurement. Fundamental science often works this way. A question that seems distant from daily life pushes technology forward because answering it demands new tools. The goal may be to understand why the universe contains matter, but along the way, humans become better at controlling beams, fields, sensors, and signals. Curiosity has a habit of leaving useful machinery behind. Still, the center of the story remains the antimatter itself. In hospitals, it is a brief signal inside the body. In space, it is a trace of energetic processes. In laboratories, it is a delicate mirror held away from matter by invisible fields. These three settings show us three faces of the same phenomenon. Antimatter is useful, natural, and deeply difficult. It is not only an idea, it is not only a danger. It is a working part of modern science. The hospital reminds us that antimatter can serve life. The sky reminds us that antimatter is part of nature's high-energy vocabulary. The laboratory reminds us that antimatter still carries secrets from the beginning. Each setting pulls the word away from fantasy and places it back into physics. Not less wonderful, but more real. And real wonder is usually better than fantasy, because it can surprise us without needing to ignore the rules. So when we ask where antimatter is, the answer is not simply nowhere. It is in controlled medical processes. It is in cosmic rays, it is in particle accelerators, it is in the aftermath of radioactive decay. It may be born in storms, stars, and violent regions of space. It is held in traps by scientists asking whether the universe's mirror is perfect. But it is not here in the form of everyday objects, because our everyday world is made of matter. Antimatter appears as a visitor, not a resident. And perhaps that is why it continues to feel so haunting. Every positron in a hospital scanner, every antiproton in a trap, every hint of antimatter from space is a tiny reminder of a much larger absence. The universe can make antimatter, but it did not keep much of it. We can use it, but only in traces. We can hold it, but only by keeping it away from everything we are made of. The mirror is real, but it is fragile in our hands. From here, the imagination naturally starts to wander. If antimatter can release so much energy, could it someday power spacecraft? If it can be trapped in tiny amounts, could future machines store it more effectively? If antihydrogen behaves almost exactly like hydrogen, could a small difference still be waiting beyond our current precision? Antimatter has already moved from equation to detector, from detector to hospital, from cosmic rays to laboratory traps. The next question is whether it will remain a rare scientific visitor, or whether it points toward technologies and discoveries that still sit beyond the edge of what we can build. The moment people learn that matter and antimatter can turn into energy when they meet, a very particular kind of imagination wakes up. It starts quietly at first, perhaps with a small thought like, "That sounds powerful." Then it becomes louder. Could it run a spacecraft? Could it carry us to other stars? Could a tiny vial of antimatter replace mountains of rocket fuel? Could the universe's mirror substance become the engine that finally lets humanity step beyond the slow, patient limits of ordinary travel? It is a tempting idea, and not only because it sounds like something whispered by a starship captain while standing in front of a very dramatic window. Antimatter really is extraordinarily energetic when compared with ordinary chemical fuel. A rocket filled with chemical propellant releases energy by rearranging atoms and molecules. The atoms themselves remain atoms. Their nuclei remain largely unchanged. It is useful, powerful, and responsible for the great roaring launches that have carried machines and people beyond Earth. But compared with the energy hidden inside matter itself, chemical energy is like warming your hands over a candle while a thunderstorm waits quietly behind the clouds. Matter antimatter annihilation reaches into the identity of the particles. A particle and its antiparticle do not merely change partners in a chemical dance. They transform into energy and other particles. That is why the idea of antimatter propulsion has such a strong grip on science fiction and serious speculation alike. In the simplest dream, a spacecraft would carry antimatter and ordinary matter, bring them together in a controlled way, and use the released energy to push itself through space. The attraction is obvious. Space is very large, and rockets are very hungry. To move faster, go farther, or carry heavier payloads, spacecraft need energy. The farther the destination, the more punishing the problem becomes. Chemical rockets are marvellous for climbing away from Earth and moving through the solar system, but they are not ideal for crossing the gulf between stars in any human-friendly time. The nearest stars are so far away that even light, the fastest thing in the universe, takes years to reach them. Ordinary spacecraft take far, far longer. If you want a starship, you need an energy source far beyond the familiar. Antimatter seems, at first glance, like the perfect answer. It is compact, it is powerful, it is physically real. It does not require inventing a new law of nature. But physics has a habit of smiling gently at perfect answers and then handing us a long list of practical difficulties, usually printed in very small text. The first difficulty is making antimatter. We can produce antimatter in particle accelerators, but only in tiny amounts. To make it, we have to spend enormous energy accelerating particles and smashing them together. Out of those collisions, some antiparticles may be produced. Then they have to be collected, slowed, and stored. The process is incredibly inefficient if your goal is fuel. It is excellent for research, but terrible for filling a tank. This is an important point because people sometimes imagine antimatter as though it were a rare mineral waiting to be mined. Perhaps somewhere in space there is an antimatter asteroid, a convenient lump of anti-rock floating politely in a region where no ordinary matter touches it. But we have no evidence of accessible natural stores like that. Antimatter appears in space as individual particles and signals from energetic processes, not as handy deposits. If you tried to scoop antimatter out of cosmic rays, you would find the supply painfully thin. It would be like trying to collect enough morning mist to fill the Atlantic Ocean, except the mist is made of antiparticles, and the Atlantic is a fuel tank for a starship. Even if we could make enough antimatter, we would then have to store it. That is the next great problem. Ordinary fuel sits in a tank. It may be explosive or flammable, but the walls of the tank can touch it. Antimatter is less cooperative. A tank made of matter cannot simply hold antimatter against its walls. If the antimatter touches the tank, it annihilates. So storage must rely on fields, not ordinary surfaces. Charged antimatter particles can be suspended using electric and magnetic fields, kept away from material walls. But a starship would not need a few particles for a laboratory experiment. It would need amounts so large that the storage problem becomes almost absurdly difficult. The trap would have to be stable, powerful, reliable, and safe under the harsh conditions of space travel. One small failure would not be the kind of problem you fix by tapping the side of the machine and saying, "Come on, old friend." Neutral antimatter atoms, such as antihydrogen, are even harder to confine. Since they carry no overall electric charge, they do not respond as simply to electric fields. Scientists can trap them using magnetic effects, but only under extremely controlled conditions and in tiny numbers. A practical antimatter storage system would require advances far beyond what we can currently build. It is not impossible in the sense of violating known physics, but it is far beyond present technology. That is a useful distinction. Some ideas are forbidden by nature. Others are allowed by nature but not yet invited into the workshop. Then comes the problem of using the energy. When matter and antimatter annihilate, the energy does not always appear in a form that is easy to direct. Some of it may emerge as high-energy light. Some may appear as fast-moving particles. A rocket engine must turn released energy into directed thrust. It needs to push something backwards so the spacecraft moves forward. If the energy sprays in all directions or appears in forms that damage the engine, the beautiful fuel becomes a very expensive way to ruin your afternoon. Designing a system that channels antimatter annihilation into controlled propulsion is one of the great theoretical engineering challenges. One possibility is not to use antimatter as the main fuel, but as a trigger or catalyst. In some proposed designs, tiny amounts of antimatter could help ignite nuclear reactions, such as fusion, reducing the difficulty of starting or controlling those reactions. In this role, antimatter would be more like a match than a log. It would not provide all the energy, but it might help release energy from another source. This is still highly speculative, and the practical difficulties remain severe, but it shows that antimatter propulsion is not a single idea. There are many versions, ranging from nearly fantastical starship engines to smaller concepts where antimatter plays a supporting role. There is also the question of safety. Antimatter has a frightening reputation, but fear alone is not the most useful guide. Rockets already carry dangerous fuels. Nuclear reactors handle dangerous materials. Human technology often involves controlling powerful processes rather than avoiding them entirely. The issue is not whether antimatter is scary. The issue is whether it can be made, stored, transported, and released in a way that is stable and predictable. At present, the answer is no for large-scale propulsion. We are very far from that. But the idea remains interesting because it sits in that strange category of possible in principle, unreachable in practice, at least for now. So could antimatter power starships. In the strict sense, physics does not laugh the idea out of the room. Matter-antimatter annihilation really does release enormous energy. A perfectly controlled antimatter engine would be one of the most powerful propulsion systems imaginable. But in the practical sense, we do not know how to make enough antimatter, store it safely, or turn its energy efficiently into thrust. The gap between laboratory antimatter and starship antimatter is not a crack you step over. It is a canyon, possibly with fog, warning signs, and a small goat looking unimpressed on the far side. But antimatter's future may be less about engines and more about discovery. In fact, this is where antimatter becomes even more important. The deepest promise of antimatter is not that it might someday push spacecraft between stars. It is that it might reveal something new about the laws of physics. It might show us a tiny difference between matter and antimatter. It might expose a hidden asymmetry. It might help explain why the universe exists as matter rather than as a nearly empty glow of radiation. Compared with that, even a starship begins to feel like the smaller dream. To search for new physics, scientists compare matter and antimatter with exquisite care. Hydrogen is one of the simplest and best understood atoms. Antihydrogen is its mirror version. If the laws of physics are perfectly symmetrical in the expected way, then antihydrogen should behave just like hydrogen in its internal structure, its light, and its response to gravity, with the appropriate reversals of charge. Scientists can make antihydrogen, trap it, and shine light on it to study its properties. Every measurement asks the same quiet question. Are you exactly the mirror we expect, or are you hiding a tiny difference? A tiny difference would matter enormously. It would not need to be dramatic. It would not need to make antimatter glow green or fall into the ceiling. Physics often changes because of small discrepancies, not theatrical ones. A measurement slightly off from prediction can become the loose thread that unravels a larger fabric. If antihydrogen's light differed from hydrogen's light by even a very small amount beyond known explanations, it would challenge some of the deepest assumptions in physics. If antimatter responded to gravity in an unexpected way, that would open an entirely new set of questions. So far, the results support the standard expectation that antimatter behaves like matter under gravity. But the measurements continue to improve. Precision is the lantern used to search the dark. Another place scientists look for new physics is in the behavior of unstable particles and their antiparticles. Some particles decay into other particles. Their antimatter counterparts decay too. If matter and antimatter were perfectly balanced in every relevant way, certain decay patterns would match exactly after accounting for the mirror reversal. But experiments have found cases where the match is not perfect. These asymmetries are real and important. They show that the mirror has small flaws. The difficulty is that the known flaws do not seem large enough to explain the great matter excess in the universe. It is as though we found a leak in the roof, but not one large enough to explain why the entire attic is full of rainwater. This hints that more may be missing. There may be unknown particles, unknown interactions or hidden processes that were active in the early universe, but are hard to see today. Some theories suggest that neutrinos may be involved. Neutrinos are already strange, almost ghost-like particles that pass through ordinary matter with very little interaction. They have tiny masses, change identity as they travel, and may have properties connected to the matter-antimatter imbalance. If neutrinos and antineutrinos behave differently in certain ways, they could help explain why matter gained its slight advantage. This is one of the reasons neutrino experiments are so important. They are not only studying elusive particles, they may be listening for the reason the universe did not cancel itself. Other ideas reach beyond the known set of particles. Some propose heavy particles in the early universe that decayed in biased ways, producing more matter than antimatter. Others suggest connections with fields that changed as the universe cooled. Still others look for clues in theories that unite forces at extremely high energies. These ideas are difficult to test because the early universe was a place of conditions far beyond what we can easily recreate. But the search is not hopeless. The history of physics has often shown that deep early universe questions leave faint traces in particle behavior, cosmic radiation, or the distribution of matter across space. Antimatter experiments are part of that larger search. When scientists trap antiprotons, compare magnetic properties, measure antihydrogen, or study particle decays, they are not just cataloguing exotic objects. They are testing whether our current theories are complete. They are pressing on the seams. A theory can be very successful and still incomplete. Newton's physics still works beautifully for many everyday situations, even though Einstein showed that it was not the final story. The current theory of particles is extraordinarily successful, but it does not explain everything. It does not fully explain the matter excess. It does not include gravity in the quantum way physicists hope for. It does not tell us what dark matter is. Antimatter may be one of the places where the next crack appears. It is worth remembering that new physics does not always arrive as a sudden dramatic replacement. Sometimes it begins as a stubborn measurement, a tiny difference, a result that refuses to line up, a particle that decays slightly more often one way than another, a number that repeats across experiments. Scientists are cautious about such things because instruments can misbehave, analysis can be difficult, and nature can imitate surprise with ordinary messiness. But when a discrepancy survives careful checking, it becomes precious. It becomes a doorway. Antimatter is especially precious because it touches so many deep ideas at once. It touches symmetry, because every antiparticle is a mirror of a particle. It touches energy, because annihilation reveals how much energy mass can become. It touches cosmology, because the missing antimatter of the universe is one of the great clues to our origins. It touches technology, because positrons help in medicine, and accelerators create antimatter for study. It touches gravity, because antihydrogen lets us ask whether the mirror falls as expected. It even touches philosophy, gently, because it reminds us that what we call ordinary matter is only ordinary because it is the side we're made of. Could there be an antimatter universe somewhere beyond what we can observe? It is a tempting thought. Perhaps beyond our cosmic horizon, far beyond the region whose light has reached us, there are places where antimatter won instead. We cannot rule out every possibility beyond observation. But within the observable universe, there is no strong evidence for large antimatter regions. If matter and antimatter domains existed close enough to interact, their boundaries would likely produce detectable radiation. The absence of such signals tells us that our visible cosmos is overwhelmingly matter. Whatever happened in the beginning, it happened broadly enough to shape the universe we can see. That makes the question even sharper. The matter excess was not just a local accident in our neighbourhood. It appears to be a feature of the observable cosmos. The imbalance was written widely, and because antimatter is the missing partner, studying it is like studying the outline of a vanished continent from the shape of the sea. The absence has a form. The lack of antimatter tells us something happened, even if we do not yet know exactly what. So the dream of antimatter starships and the search for new physics are connected by a common theme. Both ask whether we can learn to handle the deepest transformations of matter. The starship dream asks whether we can use annihilation as power. The physics dream asks whether annihilation, antiparticles and mirror symmetries can reveal the hidden rules that shaped reality. One points outward, toward travel. The other points inward and backward toward origins. Both are ambitious, both are difficult, but the second is already happening. In laboratories around the world, antimatter is not waiting for the future. It is being made, trapped, measured, and questioned now. Perhaps someday, far ahead, antimatter will become part of propulsion technology. Perhaps it will remain too difficult, too expensive, and too delicate for that role. The universe does not owe us a starship engine just because the idea is elegant. But even if antimatter never powers a vessel to another star, it has already carried the human mind a very long distance. It has taken us from the electron to the positron, from cloud chambers to cosmic rays, from medical imaging to the first moments of the universe. It has shown us that reality has a mirror side, and that the mirror is almost empty around us for reasons we still do not fully understand. And that may be the greater voyage. Not a spacecraft crossing interstellar space, but a thought crossing from the ordinary matter of a quiet room to the deepest question physics can ask. Why is there something rather than almost nothing? Why did matter survive? Why does the mirror exist, and why is it mostly gone? Antimatter may or may not become the fuel of future ships, but it is already fuel for one of the most profound searches in science. The search for the hidden imbalance that made the universe capable of becoming a place at all. Antimatter begins as a strange idea, but it does not remain only strange. After a while, if we sit with it quietly enough, it starts to reveal something deeper about the kind of universe we live in. It tells us that reality is not built only from the things that happen to be common around us. It is built from rules, patterns, symmetries, and tiny breaks in those symmetries. It tells us that the ordinary world, the one made of tables, stars, skin, air, rain, and the small crumb you might find beside your cup of tea, is ordinary only because one side of a deeper balance became dominant. Matter is familiar not because it is simple, but because it survived. That may be the most important thing antimatter reveals. The familiar is not the same as the complete. We are surrounded by matter, so matter feels like the natural language of the universe. We call it normal. We call everything else strange. But physics has a way of gently taking that confidence away from us. It shows us that for many particles, there is a mirror partner. The electron has the positron, the proton has the antiproton, the neutron has the antineutron. These are not decorations added to reality. They are part of the structure of the laws. The universe seems to allow both the particle and the antiparticle, both the word and its reflection. And yet, when we look around, one side fills the galaxies, while the other appears mostly as traces. That missing mirror is not a small detail. It is one of the clearest signs that the universe has a history. If the laws allow matter and antimatter, and if the early universe could create both, then the matter-filled cosmos we see today is not automatic. It is the result of something that happened. A slight imbalance, a subtle preference, a tiny departure from perfect equality. The world exists because the balance was not exact. Every ordinary object around you carries that fact silently inside it. A stone is not just a stone. It is a survivor of the early cosmic sorting. A star is not just a bright sphere of plasma. It is matter that remained after antimatter had mostly vanished. Your own body is made from the same ancient surplus, rearranged across billions of years into atoms, molecules, cells, breath and thought. There is a quiet humility in that. We often imagine ourselves standing at the centre of our own experience, looking outward at a universe that feels separate from us. But antimatter reminds us that we are part of the evidence. The mystery is not only in distant accelerators or deep space radiation. It is in the fact that your hand exists when, under a perfectly balanced beginning, it might not have. It is in the simple fact that there is enough matter left over to make anything at all. To study antimatter is to study why the universe had material with which to become a universe of structure, rather than a fading bath of light. And yet antimatter also reveals that destruction is not always the opposite of creation. When matter and antimatter meet, they annihilate. That word sounds final, but the process is not careless disappearance. The particle and antiparticle change into energy and sometimes other particles. The identities end, but the accounting remains. The universe does not throw anything away in the ordinary sense. It transforms. This matters because it changes how we think about the foundations of reality. At the deepest level, particles are not permanent little beads sitting forever in a cosmic box. They are excitations, events, patterns, and possibilities allowed by fields and laws. They can be created. They can vanish as particles. They can become light. They can become other particles. Reality is less like a pile of fixed things and more like a set of rules for transformation. That is not how the world feels in daily life. A table remains a table. A spoon remains a spoon. A pillow remains a pillow unless it has been claimed by a cat, in which case ownership becomes a more complicated matter. The objects around us seem stable because they are built from patterns that persist at our scale. But antimatter shows us a more fluid level beneath that stability. A particle can meet its mirror partner and become radiation. Energy can become particle and antiparticle pairs under the right conditions. The boundary between stuff and energy is not as solid as common sense suggests. The universe is not made of matter in one simple way. It is made of relationships that can shift form. Antimatter also reveals the power of symmetry. Symmetry in physics is not only visual neatness, it is a guide to what the laws allow. A symmetry says that something can be changed in a certain way, while the deeper rule remains the same. Turn a system around, shift it, reflect it, swap certain properties, and if the laws still work, then you have found a symmetry. Antimatter belongs to this world of deep reflections. It shows that particles have partners related by hidden reversals. It tells us that nature is not random in how it builds its smallest ingredients. There is pattern, there is balance, there is a mirror. But the mirror is not perfect in every way, and that may be the most revealing part of all. If the laws treated matter and antimatter with perfect equality in every relevant process, then the early universe would have had trouble leaving matter behind. The fact that we exist suggests that somewhere, somehow, the symmetry was broken. Not shattered wildly, but bent slightly. Experiments have found that certain particle processes do treat matter and antimatter a little differently. These effects are real, though not enough by themselves to explain the full matter-filled universe. So antimatter reveals both order and imperfection. It shows us that reality is built with symmetry, but also that tiny violations of symmetry can shape everything. That is a powerful lesson. The universe did not become interesting because everything was perfectly balanced. It became interesting because the balance tilted. Perfection, in this case, might have meant emptiness. A flawless match between matter and antimatter could have left very little behind. The slight mismatch became stars. The small asymmetry became chemistry. The tiny excess became oceans, mountains, nervous systems, music, memory, and the quiet act of listening in the dark. The universe is not rich because it avoided laws. It is rich because its laws allowed a small unevenness at the right moment. Antimatter also reveals something about the reach of human thought. This entire story began not with someone holding a piece of antimatter, but with an attempt to understand the electron. A physicist followed mathematics and found that the theory seemed to require a partner particle. Then experiment found it. The positron appeared not as fantasy, but as a track in a detector. This is one of the most remarkable achievements of science. Human minds, working with symbols, logic, measurement, and patience, can discover something that the senses alone would never have found. No one sees positrons in the kitchen. No one trips over an antiproton on the pavement. But through mathematics and instruments, we learned that the familiar particle world has a hidden reflection. That does not mean mathematics is magic. It means the universe has structure, and our best mathematics can sometimes describe that structure before we have directly seen all of its consequences. Antimatter is a reminder that reality may be deeper than observation at first reveals, but not beyond investigation. It may hide its pieces, but it leaves clues. A curve in a chamber, a flash in a detector, a medical image built from positron signals, a trapped antihydrogen atom held away from matter by invisible fields. Each clue is small. Together they form a story that stretches from the beginning of the universe to the machines of modern science. The existence of antimatter also changes how we think about what is natural. It would be easy to say that matter is natural and antimatter is exotic. But that is a matter-centered way of speaking. If there were beings made of antimatter in some distant, impossible-to-reach region, they might call their own substance matter and ours antimatter. They would be just as justified from their point of view. The label depends on the side of the imbalance we happen to occupy. We call our stuff normal because it is what we are made of. Physics quietly suggests that normal is often just local. That thought can be oddly calming. The universe is not arranged around our categories. It does not call things normal or strange. It simply allows what its laws allow. We are the ones who make names. Matter, antimatter, particle, antiparticle, ordinary, exotic. These names help us think, but they are not the universe itself. Antimatter teaches us to be careful with our instincts. What feels strange may be fundamental. What feels ordinary may be the result of a deep accident. What feels like the main story may only be the surviving half of a much larger pattern. There is another revealing fact. Antimatter is both incredibly powerful and incredibly delicate. Its annihilation with matter can release enormous energy, yet the amounts we can make and hold are tiny. It can help us imagine starships, but in real laboratories it must be trapped with exquisite care. It sounds like a cosmic weapon, yet in hospitals, positrons help doctors see inside the body. It is one of those scientific ideas that refuses to be only one thing. It is dangerous in principle, useful in practice, profound in theory and fragile in experiment. That mixture is very typical of deep physics. The universe rarely places its most important ideas into neat, emotional boxes. Antimatter in medicine tells us that even the strangest features of reality can become tools. The positron, once a shocking confirmation of a strange prediction, now helps build images of living tissue. A process that could be described in cosmic language becomes part of patient care. This does not reduce the wonder, it increases it. The same laws that govern particles from space also help us understand the body. The universe is connected in ways that are not vague or sentimental, but precise. The physics of antimatter can live inside a hospital scanner. The deep and the practical are not enemies. They are often the same road viewed from different distances. Antimatter in space tells us that the universe is still energetic enough to make mirror particles in violent places. Cosmic rays, stellar explosions, powerful magnetic fields, and extreme environments can create antiparticles. These particles travel, interact, and sometimes reach our detectors. They carry news from places we cannot visit. They are like tiny messengers from engines of nature that run far beyond human scale. By studying them, scientists learn about high-energy processes across the galaxy and beyond. Antimatter becomes not just a relic of the beginning, but a living part of cosmic activity. Antimatter in traps tells us that patience can turn the fleeting into the measurable. Left alone in a matter-filled world, an antiparticle is usually gone quickly. But with fields, vacuums, cooling, and careful design, scientists can hold it long enough to ask questions. That is a beautiful idea in itself. A laboratory trap is not merely a container, it is a pause button for a particle that would otherwise vanish. It creates a small window in which the mirror can be studied. It gives experimenters time to compare, test, and listen. And what have we heard so far? We have heard that antimatter behaves very much like matter in many ways. The mirror is remarkably faithful. Antihydrogen appears to share the expected properties of hydrogen. Antimatter seems to respond to gravity as ordinary matter does. Antiparticles follow the rules we expect with impressive precision. But we have also heard faint signs that the mirror is not perfectly flawless in all particle processes. These tiny asymmetries remain among the most important clues in physics. Somewhere between the faithfulness of the mirror and its imperfections may lie the answer to the cosmic imbalance. This is why antimatter is not a finished topic. It is not a museum exhibit with a neat label beneath glass. It is an active question. Every better measurement could matter. Every improved comparison between matter and antimatter could tighten the net around possible new physics. Every study of particle decays could reveal a deeper asymmetry. Every neutrino experiment could connect to the same larger mystery. We do not yet know which door will open, but antimatter stands near several of them. In the end, what antimatter really reveals about reality is that the universe is more symmetrical than it looks, and less symmetrical than it needed to be to erase us. It reveals that the ordinary world is not the whole pattern. It reveals that existence may depend on a tiny imbalance in a deeper order. It reveals that what we call matter is not simply the default substance of everything, but the surviving side of a cosmic mirror. It reveals that destruction can be transformation, that absence can be evidence, and that small differences can have enormous consequences. So as we come gently back from the edge of this mirror world, look again at the matter around you. The wall, the window, the blanket, the air, the quiet light of a screen, the body resting beneath your thoughts. None of it is as ordinary as it seems. Every atom is part of a history that began with a question still not fully answered. Why did this matter remain? Why did the mirror mostly vanish? Why did the universe lean just enough for stars to form and time to carry their ashes into worlds? Antimatter does not give us the complete answer yet. It gives us the shape of the question. It shows us the missing half, the faint reflection, the partner that appears briefly in detectors and disappears in flashes of energy. It asks us to keep measuring, keep wondering, keep listening to the small signs left by the earliest moments. And perhaps that is enough for tonight. Not a final answer tied neatly with string, but a clearer sense of the mystery. The universe is made not only from matter, but from imbalance, transformation, and rules deep enough to contain their own reflection. And here you are, made of that surviving matter, resting for a moment inside the result of an ancient asymmetry. You're not separate from the story. You're one of its quiet outcomes. The matter in your body was once scattered through stars and gas clouds, built from the same surplus that avoided the Great Cancellation. Long before it became thought, breath, or memory, it was part of the universe choosing, in the smallest possible way, not to vanish. So if your eyes are growing heavy now, let that thought settle gently. Reality is stranger than it first appears, but it is not careless. It holds mirrors. It breaks symmetries. It transforms what meets. It preserves what must be preserved. And from one tiny imbalance, it made a cosmos large enough for galaxies, planets, questions, and this quiet moment of listening. Sleep well, fellow traveller, made of matter, surrounded by matter, and held for now on the surviving side of the mirror.